think it works. Okay.
20 minutes.
Okay. I have 20 in total. 20 plus minus. Okay. Okay. Fine.
Good morning. Can you please take your seats? Have a tight schedule today. So welcome to the first AGN variability session. We're gonna start with Demetra De Cicco on AGN selection via optical variability.
Thank you. Can you hear me? Okay, fine. So, good morning, everyone. Thank you very much for the invitation for this talk. We have known for 60 years that AGN vary. Actually, we are known much longer, except we didn't know the varying sources at issue were AGN. Nevertheless, in years, we have learned a lot about AGN variability. You have heard Paula's talk yesterday, which was about AGN optical variability from a machine learning based perspective. And the first thing we should keep in mind when dealing with AGN selection based on optical variability is that it is an incomplete technique, as all the techniques that we use for AGN selection. But let's focus on the good aspects, okay, the advantages of using optical variability. I would like to stress some aspects like the fact that you are able not to miss AGN that are host dominated by their host galaxy. The fact that you can retrieve, well, we know that the X-ray emission is what you want from an AGN, right? Because it's a signature, but we also know that in practice, we don't really have it for large sky areas. So ideally, we will have it. With optical variability, we don't miss those sources that have low X-ray emission anyway. So that's definitely another advantage. And we also, in principle, are able to identify low luminosity AGN. I will explain why I said in principle in a while. Let's start. There are several works showing that using colors alone to select AGN doesn't really work very well. I mean, it works, it is fine for quasars, for type 1 AGN, but if you look, for example, I have a pointer, right? If you look at this, you see that varying nuclei can have the same colors. And we have, in one of our works dedicated to DST Cosmos data and the search for AGN in this field, we see there are several color diagrams here that were obtained using the colors that we will have with the LSST. We will be able to build several colors. Here we use just the the fact that you see here, and combining information from the light curves and the colors, you can have a more reliable sample of AGN. Indeed, what you see here, well, you see empty circles that are our label set. We use this label set to select AGN based on a random forest classifier. Essentially, we combine variability features, colors, and a morphology indicator. So the label set is represented by the empty circles. The AGN candidates are the filled circles. So what you can see is that in almost every diagram, the color of the AGN candidates are redder than the colors of the label set. And they tend to be the same color as galaxies, the green here. So essentially, what I'm trying to say is that if you use colors alone, you will miss this AGN where there is an important component of light coming from the host galaxy. While based on optical variability, when you use optical variability, you don't miss it. We also saw in the same work of 2021 that adding colors to variability information coming from the light curves, you have better results than using variability alone. And this is important to keep in mind because we will be able to do this with the LSST. Another point to stress is that APN are heterogeneous. You know that, okay, we all know that very well. And this is something that you have to deal with when you build a label set, when you try to find AGN. Indeed, here you see we use different label sets to find AGN. These are spectroscopically confirmed bright AGN. These are just like one. These are selected in the mid-infrared with the Donnelly criterion for selection. And this is a combination of both, essentially. And you see, when you have only type 1 AGN or very bright sources, you don't see any color among the top 5 features in the ranking that you obtain using a random forest classifier. Why? As soon as you add type and instead your label set colors become important. Okay, this is really something to keep in mind. And most of the literature is focused on type 1 AGN, but it's really important to deal with type 2 as well. And so part of our work is dedicated to this. Also, I mentioned that in principle, we are able to find low luminosity AGN because we all know that there is an anti-correlation between the variability and the luminosity of an AGN. Now, there are works based on space data from HST, like a series of work by Hajdinjak et al., and also this work by before. And in these works, you have good photometric accuracy, excellent photometric accuracy, and so you are able to find variable sources also when they are very faint. If you see a comparison with our data, PST, of course, we are still limited here. We don't have the greatest accuracy as the magnitude gets fainter, and so we are not really able to find low luminosity again. If you think of using different image analysis, which we will do with the LSST, things should get better, and so we should have low luminosity AGN jumping above the variability threshold. Okay, so we should get rid at least of some of the issues related to photometric accuracy. Also, another key point is that there is a correlation, we know that very well, among different bands. And so an example of this was in the paper about data talent by Čvorović et al. 2023. And work, first of part of, I mean, Paula discussed part of that work based on machine learning. This is the only part not based on that. Basically, they use the person correlation coefficient to that galaxies, quasars, and stars are different populations. And also, you can see on this diagram that they tend to occupy a specific region. Okay, and they made a test on a random set and found this period that mainly is affected by the presence of stars as main contaminants, and also very good completeness. We also have one work we haven't published yet. It's part of the master thesis of one of our students in Napoli from some years ago, where essentially he used data from the PST composite set in the G, R, and I bands. So on the left, you see sample of AGN candidates, the larger symbols, that he found based on R band variability alone. And this is the diagram where you compare with different colors. You see here you have the most reliable selection of AGN. Here you have some star-forming contamination in principle, but still this could be AGN. And see, a lot of sources are outside of this area here. But if you combine the three bands together, meaning that you require a source to be variable in R, G, and I band at the same time, you will have a much cleaner sample. It will get a 93% purity in this case. So this is an example that clearly shows how purer a sample can be when you combine variability in different bands. And with the LST, we will have 6 bands. So imagine what we can do with this simple analysis. Okay? Of course, we don't always have different colors, but there's other ways to use it. You've seen that. Also, another point that I think would be very important in the context of the LSST, what to expect, is the search for low mass galaxies. Now, there is this very interesting work by Baldassare and Gurin of 2020, where they inspect low mass galaxies and optical variability in low mass galaxies. You see, there are some details here about the sample they use. On average, they have, they have a median baseline 4 years and a median number of 65 visits. They use difference image analysis to fit the light source by means of a damper walk model, and then they obtain a probability, a significance for the source to be variable, and for this variability to be AGN-like or random variability. You see an example of their lectures here. They find a sample of more than 400 galaxies, and more than half of them have this mass below 2% to tensor masses, so they can be considered as low mass AGN. And so in this sample, they found interesting stuff. First of all, to be here. First of all, they see that the RMS, so the standard deviation of the light curves, is larger as the nuclear magnitude gets fainter, okay, which we generally observe. Also, they see that the fraction of variable AGN increases with stellar mass. There's some incompleteness issues here, and one important point is that the fraction of AGN variability definitely increases with the baseline. Now they stop here to less than 7 years. Imagine what we can have with the LSST once we cover a 10-year baseline. Okay, we will be able to achieve a larger fraction of these sources to have larger sample to deal with. Also, in this work, for the sources for which they had the spectroscopic information available, they built a BPT diagram, and this is really interesting because you see there is a color code based on the stellar mass. The sources with the lowest the lower stellar mass are here in the star-forming region, and these ones with the lowest mass are subsolar crystallicities. You see that the sources with the highest masses are in the Aegean region, but based on this diagram, you would miss 75% of the low mass Aegean if you only look at spectroscopic information to select Aegean. So this is telling you how important optical variability will be and is for the selection of low mass Aegean. Also, if you look at this diagram, it gives the probability for the variability of it to be, it gives a chi-square, okay? But essentially, it's telling you how likely it is that the source is a quasar rather than some randomly variable source. And you have all types of sources here. You have sources in the star-forming area, sources in the composite region, and sources classified as AGN based on this diagram. And you don't see any significant difference among their position on this diagram. So they are in the same part of the parameter space. So I believe it would be really important to have larger samples of this with long distance for this kind of analysis. Now, switching to our series of based on Cosmos and on ST Cosmos data, we extended recently to 11 years. We have 5 observations with some depths which didn't affect significantly most of our results, and we have 68 visits to date. I believe most of you have seen this at least once because I presented this data, but not this last season. So the reasons why we have been using this data set across the years for LSST performance forecasting studies is that we have we focus on a smaller area, okay, just one per degree, but we have a baseline that is comparable with what we will have for the LSST upon completion. And okay, the sampling is now completely different. Okay, in the beginning we had 3 days of indicators, but that's lost. Okay, and the single visit depth is pretty much the same. You can see it in the R band. And to date, we use 3 out of the 6 filters. I won't say much more about this because Maurizio Stoch, which is later this morning, will tell you about our project Timedomes that also involves other filters. Anyway, this data set is like a scaled down version of what we will have for Cosmos. And one important point is that the completeness highly depends on cadence. For example, here I showed completeness with respect to X-ray sources, okay, the most reliable reference that we have. And here we have a forecast, the very first one based on this data alone. We found that only 50% of our sources were with an X-ray counterpart were selected as optically variable. And the thing is, at this slide here, the blue line is the average variability of the X-ray sources with a counterpart to VST, VST Cosmos area. The red line is the average variability of the VST sources in general. And you see, on average the blue line is above the red line, telling us that on average the X-ray sources are more variable. So it just doesn't have enough time to jump about the variability. So at the time, is some simulations to show that with a longer baseline, we would have been able to retrieve more sources. Indeed, that's what we found here with the 3.3-year baseline, and things are a little bit better here. I'll show you numbers in a while, but first I want to stress the sample of sources that we use is heterogeneous. So we, for part of our studies, we use all the AGN that we could find in the ST Cosmos area. So you see, most of them are selected X-rays. These two samples of type 1 and type 2 AGN are by construction a subsample of the X-ray sample as they come from Chandra and XMM catalogs. So this is a specific situation. Then we have sources selected by means of the infrared and the sources that were selected only by means of optical variability. You see, there is some overlap showing what I was saying in the beginning, that the selection technique is complete, and some sources are selected only by one of these diagnostics. Anyway, here are some numbers. For type 1 AGN, things were not very good in the beginning when we only had 5 months as a baseline. Now we find 90% of them. For type 2 AGN, things were tragic because we found only 6% of them. Now we find 1/4 of type 2 AGN. So this is still an issue. I mean, we know that optical variability doesn't work really well, not always, at least for type 2 AGN. We have some numbers for the other sources. We selected infrared, where X-ray means by means of the X-ray flux type. And one important point about the baseline is here. Here we stop to 3.2 years. You see the fraction of spectroscopic AGI in the X-rays that we find rises as we extend the baseline, and this is still true when we cover a longer baseline. Things are a bit different if we focus on cadence, the importance of the cadence. For example, if you have 3.3 years, you see that there is a rise in this relation here between the number of visits that we use and the fraction of copying we are able to retrieve. While here, at some point, you reach a plateau, meaning that if you have a long baseline, this is 11 years again, so the one that we have today, it doesn't really matter if you have 10 or 40 or 70 visits, things are not dramatically different. And this is because AGN have a randomized type variability. So basically, they have enough time to jump above your threshold, even though you don't have that dense sampling. Something important to keep in mind in view of what we will want to do with LSST. Based on the variability alone, we are able to find approximately 400 AGN per square degree, which translates to 7.2 million AGN expected over the 18,000 square degrees that the LSST will cover. And another important part of our work concerns the analysis of the structure function of AGN. And again, please keep in mind that we have a main sample of AGN consisting of heterogeneous sources, as well as the different samples like type 1, type 2, and so on. And in the literature, most of the time, structure function is related to type 1 AGN. So if you want to properly compare our structure function to the literature, you need to use this one. First thing you probably see is that the slope is slightly lower here when you include type 2 AGN and sources for which we don't have public information. While here is fairly consistent with what we find in the literature. This is the definition that we use for the structure function, by the way. And if you look at type 2 AGN, things are even more different. These are all the type 2 that we could find in the field. And these are only type 2 AGN that are also optically variable. Now, here, the slope is basically consistent with 0, while here it's not, but still it is much flatter than what we have here for type 1 AGN. So, type 2 AGN seems to be the main responsible for the flattening that we observe in the structure function. But the thing is, we should, I mean, we should deal with this in some way, because if you see variability from a type 2 AGN, what does it mean? It means that you are able to see the accretion, right? You see the radiation coming from the, so why would it be different? And the main thing we can think of, the main reason, is that there is some dilution effect because of the host galaxy. So essentially, we are trying to quantify this, separating the edge component and the galactic component. You saw Angela's talk yesterday when we said that the shape didn't seem to change. In the previous work, we didn't see significant change, but we are investigating this. Probably one option is also to use fluxes instead of manual definition of structure function. So don't go through the logarithm and see what happens here. Anyway, this is something under investigation. For those of you who will attend the LSST Europe meeting, I will give a talk on type 2 AGN, so I will tell you more about this. And last thing we did was an analysis of the dependence on variability on black hole mass, accretion rate, defined by the acceleration, and volumetric luminosity. And again, I separated here the main sample and the type 1 sample using distributions of black hole masses, as well as the accretion rate and the volumetric luminosity are quite different. So you cannot expect to deal with the full sample and get the same results you get for the one sample, for example. Okay, so what we did essentially was divide into our sample of sources based on the median value of the quantity that we are having, in this case the black hole mass, and see what kind of structure function we get. Here, we don't see any significant relation with the slope or with the variability amplitude, while here we see an anti-correlation with the variability amplitude, and we seem to find a correlation with the slope. Here we see an anti-correlation with variability amplitude, while the slopes are consistent with each other. Now, I should stress that the sources with this kind of information are 264 out of the almost 700 AGN that we find in the field, which means that we need larger samples. We need larger samples, and we need synergy with other surveys to provide this kind of information that we can use for the LSST for our studies. And it's really important to have a larger sample. In principle, you might want to split the sample, keeping the black hole mass fixed in a narrow range and vary the editor ratio, but you will have very few sources. So we really need more data with this information. We know that in literature there is no general agreement about these relations, especially for the black hole mass. There is a legend here. These are just some of the works that we can find in the literature investigating these relations. And generally, there is no agreement about possible dependence on black hole mass. Well, generally, we know we agree on an anti-correlation with these parameters. So the key points of my talk. With the LSST light curves plus colors, we will be able to have more reliable samples of AGN. We will be able to find host-dominated galaxies and purer samples as we can combine multi-wavelength information. Also, we should be able finally to find decent samples of faint AGN, and so also extend our knowledge of low mass AGN. And it's really crucial that we have synergy with other surveys. We know there are these surveys, for example, I'm foremost, and we select AGN for the spectroscopic, for which we have spectra. Indeed, I should say that we stop at 20.5 magnitude, so that's not that important, but still it gives a large number of sources. In general, anyway, having larger samples is an issue, but probably the synergy will help us to get more. Okay, I'm done. I'll take any questions. Very much.
Thank you, Demetra. And my apologies for butchering your name earlier. I'm very much jet lagged and the brain doesn't work. Any question for Demetra De Cicco? Correct? Okay.
You have no idea what I heard about my name.
Okay. So I think I saw you raise it first. Start here.
Thanks. Yes, thanks. Could you go to the plot where you show the agent variability fraction as a function of the time baseline, where you show the increasing trend of the
This one?
maybe a few slides before?
Oh, okay. You mean this
So-
one?
I think still before. The y-axis is the agent variability fraction.
Okay, not in my papers
Yeah,
then.
this is
Here.
this one.
Okay.
Oh, yeah. Really don't understand what does it mean the formation points in this plot. So what is the variable agent fraction of narrow line star formation means for the
This?
squares? Yeah.
Oh, this is part of the subsamples that they investigated in the work, and so they kept them separated and show that basically for each of these types you see this fraction rising as the baseline rises, but in this case it is steeper. The rise you find is steeper, but it's just part of the samples that I investigate. I mean, and give you more details if I not exactly my work, but essentially they investigate different subsamples of sources. They also have an ancillary sample that uses a reference, and so
But that is for star forming galaxies, but not for the
so yes, no, maybe what is misleading is AGN fraction here because they're not
Yeah.
AGN. That's what we. I think they just wanted to show this maybe, and then use this. Very
Okay,
not
okay.
my responsibility.
Yes, thank you.
Thank you, Demetra. Very interesting. What I just wanted to talk about is the relation between amplitude and mass, because in recent work we have shown that the power spectrum of AGN has a break that shift to lower frequencies with mass,
Mhm.
and therefore the amplitude of variability with mass really depends on the time scales that you're looking at.
Yes, I know it works.
Right. So what we have shown in our paper 2023 is that the amplitude of variability correlates at mass on short time scales, but correlation is lost towards long time scales where you get to the flat part of the power spectrum. So it really depends on the length of your light curve whether you will find or not a correlation between amplitude variability and black hole mass.
Yes, I know, but that work not just yours about this. And the thing is, we would need longer light curves. Another good point is once we are able to combine these light curves with the LSST light curves, we will have much long mass because you see, also in the general structure function, you can see some flattening here, but we are not really sure we do see it, right? We need because there is some windowing effect that at some point drags your points down. So we need longer light curves in general, and I guess this will reflect here as well, and we will be able to see what you're talking about. I know.
About the type 2 variability, what we have found, doing the variability analysis for a large sample of type 2s with CTF data, is that the ones that do show variability, if you look carefully at the spectrum, they do have broad lines, so they're not like obscured, at least. Okay. Yeah, so there's a correlation between amplitude variability and the equivalent width of the broad lines. I just want to stress this difference between type 1.91.
Okay, that's a good point. Also, these were classified as type 2 AGN, I believe, no later than 2016. You don't really know if any of them have some properties that were not strictly type 2, right? So this is another thing to take into account, and it's indeed one. We should get new spectra for these sources, essentially, which is not exactly easy because we're talking about 122 sources, or in this case, like 1/4 of them. But they're faint, so we need a lot of time.
Sorry, I have a follow-up question. Actually, it was about regarding this work by Lopez Navas last year. So we found that more or less 11% of the type 2s were showing variability in the intensity of photometry data. In your case, I think you find 25% after.
Yes.
So where is the variability coming from? Is it a reflection, or it's just that these are true type 2 AGNs? And if
I don't really know, but I guess I remember the paper by Elena, but I think that one is, I mean, since it's CTF, it's brighter sources, right? So I assume if you extend the analysis, maybe you find more as well, right? Can't read that. I mean, it could be reflection. Yes, I actually, this result is like 2 weeks old, and it needs further investigation, definitely. So I wouldn't really say anything now.
Yes, thanks. Very, very interesting. It's triggering so many questions that we can discuss outside.
Sure.
I just wanted to discuss it is what we are saying. You really need always to keep in mind when you comparison to make sure that you're comparing apple with apple. In your table, when you were finding the correlations with the black hole masses, and you were in different authors, many of them have nothing to do with others. For example, the SIM that you are using, that was pure type 1, super bright, X-ray detected with Penstar data observed every day for months, which has nothing to do with your cadence, your sample, and so on. So we really needed to separate what is saying what based on what, and then try to find the correlation, something connection, everything. A table like that is more
Misleading.
It's
But then what do you
creating
have like
confusion.
VST Cosmos? Do you have some work similar to that that you can properly compare? I understand your
You
point.
can create some sample work, of course, they are speaking the same language, and then see what can be done for making everybody in agreement. But making a table like that without pointing out how different the samples, the goals, the depth, and so on doesn't help. It's only creating confusion.
I mean, I partly agree on that, but in spite of the differences, you still find agreement about adding ratio and luminosity. But you don't talk about this. And also, in Sims work, Sims work, they also have longer basements, right? They use they have shorter and longer basements that they sample, and they get the same results. But I understand what you mean. Yeah, I totally got it. Partly agree on that, but okay.
Okay, let's thank Demetra again.
Thank you.
So the next talk is recorded, and it's by Christian Wolf. Tell us about random walk variability, AGN, from lowest to highest accretion rates.
Good morning. By the time this recording is being broadcast, I hope we have just heard Demetra's review talk on the topic of optical variability of AGN. And so here I will present two of the recent contributions from our group. Most of the work was actually done by two of my students, my former PhD student, Chicha Tang, who's meanwhile moved on to a different institution, and my former honors student, Ashley Haitung Tan, who did her undergraduate thesis on this topic. The two students have worked on two different samples with different luminosity, black hole masses, and mean emission rest frame wavelengths. So of course, these three parameters span a 3D cube in which we can place AGN, and the two samples don't span the entire 3D cube, but sort of take up two opposite corners by being different in every of these three parameters. One sample is of high quasar luminosity, high black hole masses, typically a couple billion solar masses, and high frequency in the rest frame ultraviolet. The other sample is of low luminosity, low black hole masses, typically 1,000 times less luminous, 100 times lighter black hole masses, and with rest frame wavelengths in the optical. These samples are taken from very large sky areas, more than a quarter of the sky each sample, so they do encompass relatively rare objects as well. So the results in the high luminosity sample have been published a while ago, and we found a slope in the structure function of pretty much a half, but some suppression at the short-term end. In a recent update, we've realized that back then we over-subtracted the noise in the data, and that caused the downturn artificially. So this new analysis showed that we pretty much get a slope of a half throughout the entire delta t range of the data consistently. And we found back then that a simple parameterization where we could shift all the structure functions of the quasars onto each other would work if we assumed a characteristic time scale to scale with the wavelength squared and the square root of the luminosity, which corresponds in an approximation by Morgan et al. 2010 to roughly the orbital or thermal timescales of the mean emitting regions of accretion disks, standard thin disks. But what about the mass dependence in this? Why is there no black hole mass dependence in there? We'll get to that in a moment. So in the low luminosity, low redshift, low black hole mass sample, we find a different dependence. The plot that is shown here, the large plot, shows us the mean structure function in bins of black hole mass, but each narrow black hole mass bin actually contains a broad range of luminosities there. And of course, we then did the structure functions in bins, in both axes, binned in luminosity and mass at the same time. So that produces a larger number of panels, which I'm not showing here for today's purpose. But we can fit a dependency to all the parameters, and we get something that includes a dependence of black hole mass, and we get a slope that actually depends on black hole mass. And towards higher black hole masses, it does approach the 1/2 that we've just seen in the high mass sample. Now, that itself is a puzzling issue. I mean, if variability is driven by some timescales of otherwise self-similar disks, then a change in the slope would not be expected and more work is needed there. Now, if the slope was 1/2 in these structure functions, then the dependence seen otherwise with luminosity and black hole mass would also mean that shifting the time axis by mean orbital time scales would again make a universal structure function. But the point is the slope isn't a half, so this is still a puzzling element here. Now, the other thing is here you see a dependence of black hole mass, and in the high mass sample I did not show any such thing. How does that work? I'd like to offer some calculations that we've done recently of just standard thin disks with GR effects, assuming a spin of 0. And here you see two plots for disks of a broad range of luminosities, masses, or Eddington ratios, whichever way you want it. On the left, what's the mean emission radius? And on the right, what's the mean orbital timescale? And this is all shown for 300 nanometers as the wavelengths, as an example, but it could be done for other wavelengths as well. There are scaling relations for these. What we see is that when the black hole is fairly light, then the luminosity of the disk just sets a scale radius emission. But as we go to more massive black holes for the same luminosity disk, eventually the ISCO cuts into the disk in such a noticeable way that the mean emission radius gets pushed out eventually to very far radii. So looking at the right on the orbital timescales, it means that while the black hole mass is fairly low, as you increase the black hole mass, you hardly affect the disk. So the orbits get faster as expected, proportional to 1 over the square root of the black hole mass. But then when you get to more massive black holes, you also push out the emission radius such that eventually the orbital times flatten out and turn over and increase again. So relative to our two samples, this means in the low mass sample, we were observing the black hole mass dependence of the orbital timescales, or anyway of the scaling behavior in the variability structure function. And in the previous high mass sample, we were looking at a regime where the orbital timescales don't really depend on mass, only just in a subtle way. And so it was okay to use an approximation that did not include black hole mass as an parameter. We'll soon publish a little paper that will just offer some convenience functions for the mean emission radius and orbital timescales as a function of mass, luminosity, wavelength, and black hole spin, so that not everyone has to recalculate their entire thin disk models across the whole parameter space. These convenience functions are then not just a single power law, but they are actually smoothly broken power laws that transition from a low mass regime to a high mass regime with otherwise very simple behavior. Now, actually, for the data, we'll start looking at that next week or the week after. We'll be interested to see in the high mass sample whether we can see subtle effects of that turnover in the orbital timescale, to see whether the behavior just scales with black hole mass in some fashion, or whether it actually follows this particular prediction of the turnover, which would be really interesting to show whether the disk timescales are actually important here or something else is going on. Now, moving on briefly, damping timescales is something that we also looked at in the low luminosity sample, where the light curves are long enough that we hope to be able to see them. And once we've scaled each AGN's own structure function by a fitted timescale that unifies these, we actually see the flattening very clearly. That's shown on the right-hand side of the fit. Now, these timescales depend on luminosity and mass. And we can then also compare with the damping timescales by Burke et al. We find some detections in the range of 100 to 400 days, but also we get plenty of non-detections, or rather lower limits on the timescales. And the high mass sample doesn't help here because we have only non-detections or lower limits. Just briefly on the wavelength dependence, Nevin Kaplan and colleagues had published a beautiful paper in 2017 showing how it's steep in the UV and then flattens out in the optical. And our low mass sample in the optical shows no wavelength dependence. And of course, the high mass sample had shown a rather steep curve that was very consistent with the Kaplan paper in that regime probe there. I'll close here because I'm running out of time, and I'm just going to say that if the random walk normalization of the amplitude depends on orbital timescales, it'll depend on luminosity, and then we'll expect subtle offsets due to inclination of the accretion disk because of its anisotropic disk emission, possible effects from host galaxy dust extinction, and also effects from black hole spin and more complicated parameters of disk properties. Thank you very much.
Thank you very much. Is Christian on to take questions? So, is he on? Do we have any questions? We have time for a quick one, if there is any. No questions? Oh.
Yeah, I was wondering if in computing your structure function, you have sampling issues. So your flattening is clearly seen in the low mass object, but what about the rest? Do you see evidence of, like fake flattenings that are induced by the sampling?
I assume you're talking about the long time scale N now for the flattening. In the high mass sample, we don't see any sign of flattening whatsoever. And in the low mass sample, we see it in some cases. We actually see how, if we split it by mass spins, how the structure function really flattens out entirely. to a zero slope. But we see this only when we collapse across all the different luminosity ranges within a mass bin. If we split it out into different luminosity bins within a mass bin, then we see it in some cases, and in some cases we don't. And this produces this plot with the comparison with the Burke et al. Paper, where the results are a little bit all over the place, but tend to be longer timescales anyway than the best fitting function of the Burke paper.
Okay, thank you, Christian. We have to move on. And the next talk is from Maurizio Paolillo on the Timedomes and in-kind project, the status update. Take it away.
Hello. So I'm here to present your status update, our in-kind proposal to the LSST consortium. As Neil pointed out at the beginning of the conference, this contribution is possibly approved, possibly in the sense that we're still discussing details with the collaboration. So let me start with some. Most of my background slides have already been touched here, so it will be very fast. Just to say that we're discussing about how to properly model AGN variability. We're discussing about how to investigate the dependence of variability from the physical parameters, and we have conflicting evidence, as Mara pointed out before. This is the table that Petra was showing, but the point was exactly to show that if you're not comparing similar things, you end up with completely mixed results because it's very complicated. So I decided to use the work that Vincenzo Petrecca, who's not here because he's at the other LSST meeting, has done on revising what the variability with stripe 82 quasars, have the advantage that in terms of the wavelength coverage, part baseline, and the richness of the data is similar to what do. And using the quasar sample, which has been already studied in several other papers, sorry, buttons. Like the MacLeod sample, he studied the power spectrum instead of structure spectrum, which is basically you have from this light curve you will end up with only a power spectrum with only 3 points, which is very poor. But the average of an ensemble of quasars with the same mass and same luminosity. And so statistically, this is a rather robust estimate of the power spectrum. When you put all this power spectrum together, I will skip the details, he clearly retrieves the dependence on both the mass and the accretion rate. I think this plot shows it very clearly. Consider that in this case, these dependence are done using the power spectrum, rescaling everything at rest frame wavelength and rest frame time scales, so that you're sure that you're not mixing things up. And this is what a sample like LSST will allow you to do, to very rich large samples and plus multi-wavelength coverage and similar sampling. You can compensate for the difference in by redshift in your sample. So, and in fact, what we were discussing before, the correlation with the parameter is so good that you can plot these in a very narrow plane, and the dependence are independent. The dependence of the parameters are not mixed, are separated. And about what we were saying before about the rescaling of the Patricia was pointing out that the power spectrum of such a function are complicated. This is a plot of a sample of different masses in which you have the points that you are actually sample of your structure or your power spectrum, which you don't know if it's a bending law or just a power law because you just sampling 3 points. But for instance, even if you scale very simply by, for instance, the gravitational radius of the source without assuming anything, and also as the previous talk was pointing out, you would say that you can more or less scale and bring all the points on the same relationship. So there is an underlying dependence. And what you will actually see depends on which part of the power spectrum you're actually sampling. And in fact, this is what Patricia's work has shown. Scale all the spectra using, I think it was CTF, on similar relationship. So your dependence depend the dependent you will retrieve depend really on what you're going to sample in your lifetime. You have to be careful of which part you sample. So and plus we know that there are issues when we produce, for instance, the structure, the structure function, because there are sampling issues which may introduce all this wiggle in your structure function, may introduce artificial flattening, and so you have to be very careful also to find the flattened time scale of the, for instance, dump random walk. You need much larger time scale than where the curves flatten. So many claims of finding the flattening are then disproved as you go to longer time scales. So and in fact, this is why you ideally would like at least to put together samples of, for instance, DTF to sample short time scale and SDSS to sample long time scale to try to see if your power spectra, have exhibit flattening or not, and then investigate it depending on the mass and accretion rate. So we already discussed about the data challenge, and she pointed out that these tests that we did are mainly focused on quasar-like objects, but we're missing the bulk of the population of lower luminosity AGNs. So that's what we initially started to doing with VST project, and the method has shown mainly the result of the cosmos region, which has been sampled for the longer time. But in reality, VST has sampled also other of the deep drilling fields. From the beginning, there was a project sampling the field south and the LSST field. And so these data are partly reduced. They've been partly published, but not always in a homogeneous way and relatively short time scale. So the method has shown what she was getting in terms of X-ray based mainly on the Cosmos data set, and how you can retrieve that the variability selected object fall in the correct optical to X-ray ratio region, that when you look your diagnostic diagram in the infrared, in the optical, where you expect them, and you're also able sometimes to retrieve objects that overlap the for instance, the star forming region, so the entangled galaxies from AGN, or at least find AGN in more irregular galaxies. And shown also the structure function, the dependence on the physical parameters, but as she, Mara, and other people were pointing out before, if you have a limited sample, because you're sampling different time scale, because you cannot separate mass, then you risk of mixing everything together. So this is why we have been proposing for some time to this Timedomes project. This is the proposal. At least many people that have been involved or supported the project in the last few years, to extend the coverage in terms of baseline and of area coverage with VST in waiting for the LSST results. So what we did, we proposed to extend and do at least 4 square degree in each one of these fields, and in particular in XMM LSS, we changed the coverage to more closely match the X-ray coverage that Neil was showing us in the talk the first day. And we started doing this based on GTO time that was available to the Italian community, so bits and pieces in other programs. And then we started to apply for time specifically dedicated to this problem. So we since 20 so now we have data from 2011 up to 2022. The program is ongoing. So this is an image of how the sampling looks like, which I agree it's extremely sparse because it's one, but you can see that we're intensifying greatly the coverage in the last season. There are fields like XMLSS that had almost no coverage at all. So now we're starting to catch up on this. And it's very tricky to do this with PhD because the quality is high, but of course the telescope is much smaller. You require longer times, and so you cannot cover a very large area. But we're shifting from works like the method showed based on 1 square degree to now 6 square degree, and so we're starting to have, relatively large. So this is just an image of one of the reduction of the whole square degree on the Cosmos field. And if we enlarge, you see that we still have problem. I was pointing out the other day that in Angela simulation, the light curve are fantastic. They look good, but in real data, you will have halos, you will have spikes, you will have outliers, you will have problem with the data reduction. Hopefully, LSST will be better than this one that we're reducing by hand. But the truth is, you will have to clean up your light curve in some one way or another. So you have to be aware when we use simulation about the limitation. And yeah, this was just a zooming of a small piece. So what are the deliverables? We propose this as an in-kind because we want to give the community the full reduced single epoch images, the deep stacks optimized to the best seeing that we have, the catalogs, and possibly light curves that have been cross-correlated with LSST. So we recalibrate to that so that you can use them in combination with future LSST images. And the idea was to give more or less every 6 months release the data, and last is happening after LSST has started to give the time to cross. Now the in-kind is sort of approved, and I say sort because this in-kind is weird. It's an in-kind not that has to be done before LSST starts. So the community is discussing is approving it or not, but in the meantime we're doing the program anyway because otherwise we wouldn't have the light curve. And the latest suggestion was to have a collaboration workshop to assess the needs of the community. Really, there isn't a lot of flexibility, so we're doing the observation now, but every input about how to optimize this is very welcome to try to get the best strategy that will suit everybody's. And there are many challenges, of course. We have a problem in terms of manpower because we have to use all the data on our own. Woman power, work. I wrote workforce, right? So which I liked more. Yes, but I changed it. You're right. Sorry. And and luckily, Marta just joined our group, which will be in charge of the scheduling, doing part of this reduction. And the efficiency of the scheduling has been sort of low. It's complicated to schedule now that EST is handled by the Italian community with all the other programs and to get the monitoring program going. And there are data reduction problems, for instance, with the stability of the data reduction. In particular, we are having issue with the overload. The Italian community now is taking care of the reduction of all the VST data, and this is creating an overload. And hopefully, in Naples, we're trying to set up, Massimo Brescia is trying to set up a data center in which we can speed up the reduction, import the VST database, and do everything in-house without relying on the current pipeline that is in the Netherlands. And also, there have been problems with the photometric quality. For instance, one of the CCD has not been working for years. Then when we did the first 4 square degree, we looked at the data and we said, oh, great, we choose the perfect dithering pattern because there's no hole and no degradation of that. Then we became suspicious that it was too good. And so we went and we asked ESO and say, look, it doesn't seem to be a problem with the CCD anymore, which was off. And they looked and said, oh, really? Yes, it came back up. So we had to inform them that it came back up. But the problem is that it's not very well characterized now in terms of the photometric performance. And the masking is mostly manual, although I will show you that there is something that can be improved. But this is an example, for instance, we're doing the data reduction and we discover, for instance, the data reduction, if we do the magnitude difference with the reference epoch of a new, sometimes you find things like this. So some CCDs are way off the rest. And then we discover that redo recalibration for every night, then you can get a much better. Still, there are gradients, but much better control on the photometric uncertainty. So this is a massive work, and this is an example. This is your magnitude difference with respect to a reference epoch. The shift is due mainly to PSF variation, but you can see the photometric accuracy, and you can see that the old data were here, and the new data in the beginning were up here, so we're way up in terms of 7% of photometric accuracy. But then we started working on the data, and we brought this line down to here, doing new data reduction, do some signal now and down here. So now we're getting light curves which are much closer to the past one, and we can homogenize the whole data set. So things are improving. Also, we to address the problem of these spikes, outliers, we're doing using convolution neural network to identify problems in the light curves. So in this way, you automatically identify issues with bright stars, with tracks that were not properly subtracted, with hot columns that will affect your data, trying to automatize the process so we can clean up things faster without, because it's just impossible to do it manually. So my conclusion is that with this large survey, we will be able to derive properly the dependence of physical parameters and rescale everything, hopefully to the depth of LSST and similar also in lower luminosity AGN in Galaxy. And we're trying to do with Timedome. We hope that it's approved, it will benefit our community. So we welcome any feedback on this, because we are really working on the data, and you're welcome to ask for update or the data as they come to work together on this. Thank you.
Thank you very much, Maurizio. We have time for a couple of questions.
Thank you. Thanks very much. I was just wondering what pipeline you're using to process the VST data, and whether you use the LSST.
No. So we're using the AstroWise pipeline, which has been one of the two pipelines that historically have been used. We started looking to using the LSST pipeline. That was one of the possibilities also for Rainkind. There is a problem about the ingestion of the data into the pipeline, creating the proper butler. So we played with it a little bit, then we stopped, but it would be ideal to use this as a test to see how it performs to the LSST pipeline. So it's our, let's say, dreams. It's just a problem of manpower and maybe some help from the LSST community to ingest the data.
You've got this guy here.
Yeah.
Speak with him.
Great. That's exactly what we needed. We had in mind for some time.
We have time for one more question, if there's any.
Are you planning to provide difference photometry for all the sources?
No, not directly. We had in mind that if we could ingest through the LSST pipeline, ideally we'd like to see how that does the difference. We've done testing of this. We worked. It's tricky. We were working with the Supernova people that are using the same data, and they're doing different imaging. It's not always easy, because they use different light curves. It's completely different from us. Then, because they don't have a constant luminosity, right, of the agent, which you want to retrieve to get the intrinsic properties. And so they throw away information that we actually need. So this is a tricky part that, of course, any help on that is welcome.
Okay, thank you again, Maurizio. Our next talk is from Temple on extreme AGN variability in LSST.
Okay, can you hear me okay? It's too big. Is that better? Can you hear me at the back? Okay, I'll talk loudly. So yes, hello everyone. For those of you who don't know me, I'm Matthew Temple. I've recently moved to Durham in the UK. And so I'm listening to all here and making everything move smoothly. It's great to be here in Turin. So today I want to talk a bit about variability in LSST. We've had lots of great talks about variability. There's been out more today. But you know, there's kind of, in my head, there's two bits of variability science to LSST. There's all the big population stuff, characterizing AGN across different wavelengths, cosmic times, different black hole masses, and that's all great. I don't want downplaying of that. But also, what I'm interested in is the weirdos, right? The wacky objects, the outliers, the interesting things that you might not expect to see, the unpredictable events. And so that's what I want to talk about today is, how can we think about efficiently selecting and following up weird AGN variability, extreme AGN variability, and maybe learning something new that we didn't know before. So, we've already had some great introductions to AGN variability in general. I'm sure I don't need to convince this audience that AGN are interesting for their variability. I just want to highlight the fact that the strength of variability we see in the restrained UV and optical could already be a challenge to standard discriminants, right? The fact that we see such strong variability is telling us something about the physics of the accretion flow. It's telling us something about how the power and the accretion flow is being propagated. And this is kind of, I think, a problem that as a community we need to keep in mind, right? This is actually telling us about the physics of the central engine. And so, where am I going with this? LSST, AGN variability can be inferred on all time scales, as we just heard. Actually, the longer we look, so the x-axis here, the longer we look, the more variability we see. It's a nice correlation. So we see, where you're using different surveys, different timescale. The key idea here is that actually LSST is going to help us probe the weird objects outside this parameter space. And so when we look at AGN variability, when we're trying to say, well, what is an unusual variability event, we need to have in mind what is a usual variability, what's the baseline. And effectively, just because it's varying by 5 sigma in the LSST alerts gene doesn't necessarily mean that it's unusual. As we heard yesterday, most AGN do vary and do produce alerts already in CPF, right, above some magnitude. And so when we're trying to select unusual rare variability events from an alert stream, we need to have in mind some sort of baseline. And so I've just put up, there's lots of people in the room expert on these areas much more than I am, but some of the unusual or interesting variabilities which you might try and follow up specifically. Some of these I mentioned yesterday, some will be talked about later today. I'm going to focus on changing look, changing state AGN at the top, because that's where I've done some work myself, but bearing in mind that this is a more general talk about how are we selecting interesting AGN. So for those of you who haven't, don't know much about changing look AGN, just a brief introduction. Obviously, Ilsang and Claudia are going to talk about this much more this afternoon. Changing look AGN are AGN where we see significant changes in the broad flux. In this case, this is the broad H alpha line over timescales of sort of years, decades, or even less. And so this is an example of an object selected from the Swift-Back survey. So it's selected ultra-hard X-rays. And when we go and look at the archival spectra for this object, we see that over a period of less than 10 years, the broad spar emission line is just completely switched on and appeared. And so this is happening orders of magnitude faster than the viscous timescale. And it's a real puzzle as to what's happening to actually allow these changes to be happening right in the central stage on short timescales. Just to highlight for this object, we have the Swift-Back light curve. So this is the 15 to 150 kV X-rays, where we're seeing that actually the what I call the narrow line epoch here back in 2009 was corresponding to the lower flux in the X-ray light curve, and the broad line epoch 16, but after the accretion rate had increased and the X-ray luminosity had increased. So what do we know about these objects? Just some highlights of my work. We've looking at the Swift-Back sample. These are local AGNs, about 1,000 of the most luminous AGN in the hard X-rays. We see that something like 3% of them are showing variability within 15-year timescales, where their broad lines are completely switching on or switching off. However, this is kind of unresolved already, in the sense that we're limited by the cadence of the follow-up at the moment. And so it's entirely possible that we're missing some objects which are turned on and then turned off again, turned off and then turned back on again before we've had a chance to observe it. So this is possibly a lower limit on how many of these AGN are actually doing really interesting physical changes on very short time What we know so far is these tend to be lower accretion rate. I'm sure Ilse and Cloud are going to talk about this later. It seems to be a relatively common phenomenon, but potentially isolated for low accretion rates sources. So I want to switch gears to thinking about, well, how can we start to think about finding these sources from LSST? So I'm going to use an object from SPSS to demonstrate a point here. So this was a change in the page end discovered in Sloan 5, and this work led by Grisha Zelton at Tel Aviv, along with Benny Trachtenbach, where we saw the archival Sloan spectrum 2001 was this bright blue type 1 AGN. Sloan actually observed this in 2016, which is the green spectrum, which you can't really see, but it's building in the middle here. And there's still some broad line flux. You can see the continuum is getting a little bit weaker. And Sloan 5 switched on in 2021, April, and it was right down here at the bottom, right? At which point they said, okay, this is kind of interesting, let's look at it again. And so I can get follow-up spectra in May here, and then within less than a year, come back up to this intermediate stage. So just to illustrate this from the light curve, this is the CCF GNR light curve in the red and green here. Sorry, green and red. So this is the archival 2001 spectrum. This is 2016. You can see the light curve is peeling up quite happily, and then there's this big dip in light curve, and that's when we first observed it in 5. So this is all great. You're probably saying, what's the problem? We can see these things in light curves, and then we can observe them. But the problem is that Sloan 5 didn't actually know about this light curve when they switched on and decided to observe this. So this is completely separate. And if we'd not seen it for a couple of months and just observed it here, then we wouldn't have got a spectrum at the bottom of this dip at all. We'd have missed out on all this interesting physics, which actually happened within a couple of months, right? And so my challenge to the community as well, we're going to do all this amazing science from the data releases, from the light curves, and we've got long light curves. But actually, what can we be doing with the alert stream? What can we be doing in the same night even, as an alert being issued? This would have been an alert here. What would the spectrum look like if we'd got the spectrum right here? So how well can we refine our selection algorithms? How promptly can we get follow-up of these objects? So just to finish off the point about Sloan 5, SPSS is trying to do this on a statistical sample, but they're blindly selected. They're just following up known objects. They're not trying to identify interesting ones. They're trying to do a broad brush approach. Sloan 5 will find more interesting sources like this, I'm sure. That's great. But it will also miss a lot of interesting sources. At the same time, Sloan 5 is going to finish in a couple of years' time. It's not going to continue throughout LSST. And Claudia mentioned this yesterday. There's what might happen next. But fundamentally, SDSS is only a 2.5 meter telescope, and it's really limited to sort of 19th magnitude to get prompt follow-up. And LSST is going to find many, many fainter AGN doing interesting stuff that I think is worth thinking about. How can we follow it up? And that's where maybe large facilities could be useful. So why timely follow-up? Well, spectra give you the who, the what, and the where. First and foremost, you get a redshift. If you don't know what it is already, it tells you how far away it is, what luminosity is doing. But also, more importantly, spectroscopic follow-up can start probing the physics. Right? It can tell you what might be going on. It can classify the event. Is it a change in absorption? Is it accretion physics? Is it some sort of jet activity, beaming? Is it something else entirely? And we can do this with things like borderline strength, and continuum slope, and all that good stuff. But then also looking ahead, multi-wavelength follow-up can also help disentangle some of this stuff. And so that's the motivation for why you need to pull these things up. LSST on its own is great, but it's not going to give us the full picture. And for new and interesting AGN physics, I think it's really useful to have the full picture. So why is this hard? And the hard point is that at the moment, changes, we know that changes in photometry are one-to-one correlated with changes in the spectrum. So this is an example from Matthew Graham's paper in 2020, where effectively the x-axis in both of these plots is the fractional change in the broad H to the line flux, and the y-axes are a measure of the variability in photometry of the light curve. And so you can see that all these highlighted points are the changing look objects, candidates, and they're kind of scattered vertically, right? It's not like everything up here is varying a lot in the light curve and varying in the light spectrum. So you've got this huge spread of actually, just because something's displaying interesting changes, doesn't mean that a simplistic just measuring the change in the light curve is going to tell you to follow that object up. And this is only going to get worse in LSST, right? Because LSST is going to give an alert for every sort of 5 sigma change in poetry. And as I said earlier, that's going to be most AGN in the sky at this point. And so just because you've got 5 sigma alert in LSST doesn't necessarily mean this is a really, really super interesting AGN. You should get spectrum straight away. I know LSST is already thinking about this, and I think as a collaboration, it'd be good to talk more with the brokers and understand what their classifiers are going to be for the alerts, but also think about what input we can be providing as collaboration to help them refine those classifiers. So I appreciate this as a talk with more questions than answers, perhaps. As I said, this is, Paola's work has already been starting to think about this, and it would be remiss of me not to highlight this. If you've not read this paper, then please go away and have a look. It's really interesting. But just to wrap up, so LSST is going to find lots of really AGN, but I think we've got a question we need to address within the community is what's really interesting versus what can wait until the end of the data release, right? And so there will be some objects that hugely benefit from spectroscopic follow-up. I'd really like to see, can we challenge ourselves, how quickly can we how quickly can we follow them up? Because I think the faster we can get spectra for some of these sources, the more we can look at them. But to do that, we need to figure out how to identify them. And so that's, yeah, happy to hopefully promote some discussion and take questions.
Thank you very much, Matthew. We have time for questions.
More than a question to you is probably something that we can trigger now and discuss more later. When we do variability, and I really do not know the answer. So when we do variability using images, we extract the entire flux and then we look at the variation. When we classify an object as a changing state from spectroscopy, we are using data that every time can come from long state spectroscopy or fibers. There is an issue with the pointing that depending on how extended the object, depending on where you are pointing, you may have something that is not necessarily the center. So sometimes what we call variability is just a mispointing of the slit of the fibers or the thickness of the fiber compared to the slit that normally was 1 arsec. All the work that we are doing in looking at the properties from the spectroscopic point of view, how much do they take into account the possibility that the changes are human changes and not really on the changes of the object?
Yeah, no, it's a great point, Mara, and this is a huge problem that when you're, especially if you're comparing with archival data, and as you say, it could be a 26 arc slit, and you've suddenly got a 3 arc fiber from your new survey. And so that's why actually it's really important when you're trying to classify these objects to be also using the light curve at the same time. So I mean, there was a paper from the Dark Energy Spectroscopic Instrument, DESI, right, where they put the refereed version on the archive, claiming to have 100 and something change KGN, and by the time it had been refereed, that number was significantly lower because the referee told them to look at the light curves. So this is definitely a problem. I think the community is becoming more aware of it, but you're right, we should definitely be thinking about. There's always instrumental effects, especially when you've got different observations and telescopes.
More questions?
You said that dramatic changes in emission lines do not always correlate with other properties. Do they correlate with X-ray change?
Depending on the X-ray band, sometimes yes. I don't know if Claudio's going to talk more about this later. Claudio's the expert. But sometimes yes, but not always. But it depends on, is it obscuration, is it change distribution? That's where having the multi-wavelength follow-up can really help you probe the physics of what's going on.
Let's take Matthew again. And we're moving to the final talk of the session, which is going to be online from Alexander Messick on a large-scale search for photometric variability in dwarf galaxies using the Young supernova experiment. Alexander, can you hear us?
Hello? Hello?
Hi, can you hear us?
Yeah.
Okay, great.
One
Start
second.
sharing.
One moment. It's not letting me share my screen. Let me try to back out and then join again.
Okay.
It says I'm sharing. Do y'all see anything?
Nope.
No. No. Um,
So, if you cannot share, maybe we can share and you just tell us to flip slides.
Okay.
no. Yeah, okay.
Okay. Hello everyone. Can y'all see and hear everything right?
Yes.
Okay, perfect. thank you all for giving me this opportunity to talk. I'm sorry that I have to give it from the hotel room. I have a bit of a stomach bug right now. So anyway, I will be presenting some preliminary results of a large-scale search for photometric variability in dwarf galaxies using data from the Young Supernova experiment. I am Alexander Messick. I'm a PhD candidate at Washington State University, working with Vivian Baldessari. Next. Next slide, please.
Yeah.
We changed. Oh, it's I guess it just takes a second. It's still showing me the title slide. Okay.
I guess it is.
Yeah, it's still showing me the title slide. Okay. Not showing. Okay, I guess I'll just go on and trust that y'all are seeing a slide called SMBHs, IMBHs, and AGNs.
Yes.
Okay, cool. Anyway, so kind of a bit of a motivation of what we're trying to do with this project. We all have observed and know much about supermassive black holes. We know that intermediate mass black holes are much more elusive for multiple reasons. So on the right is kind of, oh, and on top of this, we don't know how either of these objects are formed. On the right is kind of a cartoon summary of 3 different pathways that we have ideas for of how these supermassive black holes came to be, given the absence of intermediate mass black holes. The most important difference between these 3 models is the subplots on the right, which depict that they have different numbers for black hole fraction, occupation fraction, and then black hole mass as a function of galaxy host mass. So we can try to constrain those 3 values, especially in the low mass regime for galaxies, to try to get an idea of which of these, is the most likely way that these objects came to be. So again, because intermediate mass black holes are more difficult to detect just intrinsically, astronomers have begun using things like AGNs to try to come up with indirect methods to detect these objects. Next slide, please. One of these tools that we have used to begin detecting AGNs in these objects is variability. So AGNs are known to vary stochastically across the entire electromagnetic spectrum. We've known for about 1 or 2 decades that this variability can be well fit to a GAMP random walk. And that makes it cheaper and more accessible and easier to use than some of the other methods for AGN detection. So the 2 plots on the right are one object that is not and one object that is photometrically variable with this AGN-like variability. And then on the bottom, on the left is what's called a BPT diagram. It is just a diagram that plots the ratios of certain emission lines. It makes empirical cuts to try to classify the emission as being dominated by star formation, AGN emission, or some composite of both. And then in the center, we have a Venn diagram from my 2023 paper in which we looked at 14 photometrically variable objects, and we followed them up in the X-ray and a few other AGN detection methods. And as you can see, there were only 2 of the 14 objects that were detected by all of the methods we used, whereas the majority of them were only detected using the photometric variability. Next slide, please. So with this AGN variability, this is kind of where the LSST Rubin comes in, and the Young Super. So these are both AGN variability is within the regime of time domain astronomy. Anytime you have large amounts of data, of photometric data, available over large spans of time with a decent enough cadence, you can do this kind of analysis. Like I said, that makes it very conducive to for the LSST Rubin Observatory. And as I mentioned, the Young Supernova experiment. So the Young Supernova experiment uses data from the Pan-STARRS telescope, which have a fairly large sky viewing, and a 3-day cadence, which kind of makes them, again, perfect for this time analysis. So what we did next is I gathered 60,000 targets from 3 sources: the NASA Sloan Atlas, the Sloan Digital Sky Survey, and the Galaxy and Mass Assembly. And we were looking for dwarf galaxies and low mass galaxies below 10 to the 10 solar masses in stellar host mass. And the histogram in the bottom right shows the masses of our sample. And as you can see, there's that dotted line at 9.5. Usually that's the accepted cutoff for a quote-unquote dwarf galaxy. So we specify that we extend this up to 10 to the 10, and that extra expansion actually comprises about half the sample. So from the superconductor experiment, we request difference in stack images, and then we recombine those to get a positive value that we can convert into magnitudes. And the reason that we do this difference in stack imaging is when you do this kind of time domain analysis, it is useful to degrade your images to a common resolution to avoid artifacts like difference spikes and other such things. Okay. Next slide. So the main software that we use to determine and fit these to Dan Frannon walks is called QSO Fit. This fits a light curve to a Dan Frannon walk and provides 3 significances. First, that the object is variable, then that the object is specifically APN variable, and then last, that it is variable but in a random way. And we use those 3 values to determine kind of our baseline against Boolean candidacy. To kind of, sorry?
That's somebody called.
What was that? Keep going. Okay. So we took these values and we did what's called bootstrapping them, which is because they were given some uncertainty, we sampled the values plus that uncertainty, plus like a random sampling of the uncertainty, and then analyzed them 100 times to get a kind of distribution of the final parameters. Again, that's called bootstrapping. And then we also calculated something called a fractional variability, which is a measure of the variability of the light curve, which has been associated with AGN activity in the past. Next slide. Okay. So from those values, we first selected all of our AGN, and then we inspected them by eye, and we found very many quote-unquote dubious objects. So we decided to apply further AGN selection criteria. So first was the bootstrapping test. Since we already had bootstrapped our values, we just wanted to make sure that that any object that is selected is an AGN in at least half of the bootstrap iterations. It is less than half. If it is less than half, we throw it out. Next, we do what is called the point test. So for every light curve, we find the mean, and then we find the point that is farthest away from the mean and remove it. Of course, this is all done after a 5 sigma clipping. So this is like an extra necessary step to get really clean light curves. On top of finding the point farthest from mean, we also found the point with the largest uncertainty and then removed that as another test. Both of those are called the point tests. And then finally, we just plotted the mean magnitude versus standard deviation of magnitude for all of the analyzable light curves that we had, and then we fit a simple line. Anything above this line, we said has excess variance, and then anything below this line, we said did not. So we select for these 3 criteria and find 5,267 individual light curves that satisfy all these criteria, which belong to 3,100 objects, I believe. Next slide. So the next thing that we wanted to calculate from our AGN results is the AGN fraction as a function of mass. On the right, you can see we have our results binned by mass, host mass, and the mean R-band magnitude, mostly to show that if we were to simply bin by mass and then calculate the AGN fraction there, we would actually introduce a magnitude bias. So on the left is what we try to do to counteract that. we fit a Gaussian. So first, we split all of the masses into mass bins at about half dex, and we went to the heaviest bin, 9.5 to 10, and we fit that distribution of the magnitude to a Gaussian. That's the bottom right corner on the left. So given that fit Gaussian, we then go back and fit all the rest of the bins with their own Gaussians with the same center and standard deviation. So all six Gaussians shown on the left have the same center and standard deviation, and we adjust their amplitude so that they fit underneath the like result distribution as close as we could get. Next slide. And so on the results of that are shown on the left. As you can see, we don't have very many points, and we have this like red dotted line, but I don't know if I would necessarily trust that per se. However, given our results, we do see like a positive slope for the AGN fraction in this regime. And I kind of have just the like formula that we found that we fit underneath. We have a slope of about 1.1 and then an intercept of about -5. So this could indicate one of the particular pathways that we mentioned earlier. I would say direct collapse or let's see, gravitational runway, I believe. But again, these are not very sturdy. I don't know if I would trust this AGN fraction slope per se. Next slide. And we compared our known AGNs against the NASA Sloan Atlas and what is called the Weslesley catalog. So my colleague Eric Weslesley is creating a catalog of all known AGNs bona fide from dwarf galaxies. And so we use that catalog and the NASA Sloan Atlas to compare against. We found 213 AGN candidates overall that were not found in either not found as AGN in either catalog, and we only have one object. Funny enough, that is classified as AGN and dwarf in all of our sources. And so just to be clear, on the left is our target list our list of all galaxies that have at least one photometrically variable band. And then on the right is all galaxies that are photometrically variable in multiple bands, which is our list of AGN candidates. Next slide. So with these AGN candidates, the next thing that we wanted to do was to check their spectroscopy. So we do so with Pi2SOFIT, which fits multiple lines simultaneously, does the continuum, and it is designed to do this specifically for AGN. So on the bottom center is kind of like the entire output of one of these, and then on the right are some more examples of galaxies we found with broad H alpha emission. Next slide. So with that broad H alpha emission, we use that to calculate the black hole masses from these objects. And then we compared them to some populations. From the RINES 2015, we have a population of local galaxies and a classical population, but also a population of maser dwarf galaxies from green 2016. Most of our objects fall kind of along the RINES 2015 local distribution shown in green, but many fall higher than that, even a few objects falling above all relationships entirely. Yeah. Next slide. You have 2 more minutes. Okay, I will go quickly then. Okay, so with on top of the black hole masses, the next thing that we did with our spectroscopy is we fit to a BPT diagnostic. As I mentioned earlier, this is just a plot of the ratio of certain emission lines with empirical cuts to classify the emission. So from our AGN candidates shown on the left, only 5, or excuse me, on the left is the dwarf AGN candidates, and on the right is all AGN candidates. So on the left, only 5 AGN candidates were actually classified as AGN by this diagnostic. And then on the right, you can see that only 37 out of all of our AGNs were classified by this way. On top of this, we also show the galaxies with broad H alpha emission as red X's kind of throughout both of the graphs. And again, the majority of them still fall in the star forming region, which is to be expected. We already kind of know that this BBT diagnostic does not work great for low mass and low mid LST galaxies. Finally, we wanted to compare the dampening timescale associated with a damp random walk. And to do that, we use this software called TauFit. It fits the light curve as a Gaussian process, and again, it finds that dampening timescale as well as a dampening length scale. And kind of a corner plot of those values is shown on the right. But on the left, we have those results compared to the relation found in Burke et al. 2021. Similar to that paper, we see general agreement with a large amount of scatter. Yeah, next slide. Yeah, so we have a total of 1130 aging candidates, which is about 2.5% of the overall number of light curves we were able to analyze. And that gets a spectral variability typically about between 0.05 and even up to 2. So on the right is kind of just like this this breaking down of the recursive sets of QSOs and AGNs that we found. And that is all. Thank you very much.
Okay, thank you. Okay, thank you. We have time for one question.
Yes, thank you. I wanted to ask you about the black holes because your mass was 10 to the 10, but then most of the black hole masses you found were to the 8 to the 9 masses. Is that correct?
I can only partially hear a question. I heard that the galaxies I selected were up to 10 to the 10, right? So what was the question?
The black hole masses.
Mm-hmm.
They seem to be quite high. Hello? Hello? Can you hear me?
Okay, so I now see in the chat it says that the black hole masses were too high. Yeah, that it does seem like you have a point because there's even like one value where the host mass is 10 to the 9.1 or so, and the black hole mass is 10 to the 8.1. Yeah, we originally thought that these were overestimated, and it's possible that they still are. These are some preliminary results. I can't remember what we did to fix that though. And again, we can just go back and check those like individual high galaxies to make sure that we're not fitting the black hole mass strangely.
Okay, thank you very much, Alexander, and let's thank all the speakers of the session. Claudia, do you have announcements? Okay, so off to the coffee break.
everyone. No se sente. Sí, sí. There is no. Yeah. Is there? Sí, sí. Perfect. Thank you. Hello, everyone. Welcome back. We should get started. Now?
Not just to get in touch later at lunch because they can.
Okay, you can ask a question.
Now, I'm just asking if there are other people have their wife of companion joining the Matini tour later, because in that case, maybe at lunchtime we can arrange for them to join us together.
Okay, get to Maurizio if you need to bring another person to the event later on. So thank you all for joining us to the coffee break. I'm very happy to share this exciting session dedicated to the innovative tools that we are all about to start using massively. So I'm very I appreciate that I'm chairing this session, and unfortunately have to share some a little bit sad news that our student Iva Čvorović, who is a student of Anđelka Kovačević, got seriously sick last week. We got a call from parents, and he is hospitalized, and we hope that she will get better. I mean, we have no news until now. But we discussed with Claudia, and as a chair of the meeting, she agreed that I can briefly present her work on her behalf, because we really want to, in this way, give support to her and share the news that her work was presented here to her parents, and hopefully that to give a bit of strength from our side. So without further ado, I'm going to share myself now. If I start talking for 20 minutes, you just say that. Yes, I'm going to talk about a very exciting work about applying basically conditional neural processes and self-organizing maps on quasar light curves, and on light curves in general. And this is the work done within the PhD thesis of Eva, and I know very well this work. I mean, the PhD thesis. So I think I will present it in an appropriate manner. So Eve, just to put it in the content of large data volumes and big data, we all know that with all of these missions, and the LSST is right there, and the other missions coming, we really have to basically, we are entering not really the first, but actually the third wave of application of machine learning tools in astronomy. And basically, we are all going in this direction that basically no human intervention is needed, because we are really entering a large data set. And I am happy that this and other talks will address these topics. So some of the recent research on machine learning application is basically showing all the challenges and applications, especially in light curves of AGN, of neural processes, and the continuous functions that can represent discrete functions that we actually have as light curves. And the most maybe challenging thing is the computational time, and that we need to find processes that can pass this handle big data sets. And one of the family which has been shown to be a good application tools are neural processes and the family of neural processes. So the motivation for this work done by Eva was basically, when we talk about quasar light curves specifically, these light curves have a lot of challenges to be modeled with a unique tool. So, for example, here you see four light curves with specific features. We see light curves with increasing. We see light curves that are changing dramatically. We see light curves that are decreasing. We see some periodic acceleration, quasi-periodic. We see, and then of course there are many technical issues and challenges like observational gaps, inhomogeneous data, number of points, cadences, and so on. All of these things are quite a challenge to tackle and solve with one specific tool. And as I said, the data are complex and they're showing various, let's say, topologies. And with this work that was done by Eva, under the supervision of Anđelka Kovačević, we wanted to find some approach which is basically data-driven and that is going to be fast enough. For example, the conditional neural processes with compared to the bullshit processes I have shown to be much faster. And this science case was also presented within the LSST white paper of let's say science cases from data from over the software to science with Rubin. So the two testing hypotheses which are being addressed within this work are basically how can we apply neural processes on quasar light curves basically, and to lower the dimensional space and basically do the representation of the light curves through the neural processes and basically whether we can represent the light curves in the lower dimensional space with the neural processes encoded. And the second hypothesis, which was another input from the community, is that some sort of clustering or organization of the data set prior to applying the neural processes is required. And here, the hypothesis that has been tested was whether the self-organizing maps could be used basically to the raw resolution of the parameter space of quasar light curves, but preserving the features and basically representation of the light curves. And these are all being presented in the publications by Eva. And here is the architecture. I won't go into of course, into details. What is important that based on some sort of contextual points in the light curves, we want to reproduce targeted points within the light curves. Another feature that was introduced in the methodology was the application of self-organizing maps to perform some sort of clustering prior to applying the neural processes, and this has been addressed with a master student also at the University of Belgrade, and Aman Raju will present this in the next talk. So the data that has been selected to test this methodology was from assessment survey, so the automated survey to Supernova, which had a baseline of 2,000 days and well-populated light curves. So here is the histogram showing the number of per light curve of the assessing data, and this was all optical data, of course. So we tested it on around 200 light curves. So as I said before, doing the neural processes, applying on application on the light curves, the data were clustered, and this is the result of the application of the self-organizing maps, and the final result, you can see it on the right. This is the process resulted in 16 clusters after doing the, let's say, preparation of the data, like removal of the outliers that you can see on the left light curve, on the left plot. So here are the clusters, these 16 clusters, and what is important to note is that basically we can group them, we can characterize them with the different properties of variability. For example, few clusters were denoted as clusters with low variability, then we have moderate variability, high variability, and for example, cluster number 8, that's be this one, who is showing a unique sort of type of variability. And once you apply what is really shown here, first result, once you apply a neural process tool that is part of the Serbian in-kind contribution, you can see the results after training of certain clusters. And the left plot, you can see it on the all light curves, and the second plot after separating on different clusters. And here are some more examples of the result. Again, left side plots are without clustering, and the right hand plots are after separating the data samples into clusters. And obviously, the results of applied neural processes, the QNPy package, are much better. So to conclude, this algorithm developed within the PhD thesis of Eva was basically base in-kind contribution of the Serbian AGN group, which is the Rectangle Software in-kind contribution to the LSST, and the package which was being released on top of this architecture developed by Eva, the QNPy package you can find either on it can be easily pip installed, or you can see this GitHub link. And what is really important is that this the whole strategy of the tool is that it's data driven. There is no a priori knowledge required on the data set, and you can apply this to any time series. Actually, we have a successful application of this package on time series coming from medicine or other science field. And there are further upgrades of the packages, and this will be addressed in the next talk by Raju. Thank you for questions. So Anjaka is also here, and she can help in addressing the question as a supervisor. She is very much aware of it. Paola, please. And now I'm the chair. Okay.
Thanks. If you can go back to this, the final Lakers you were showing with the modeling. So these short time scale variations are just due by the photometric errors, or this is real variability that is not well described by them?
Yes, thank you. That is a great point because we are here. We are seeing here the conditional neural process, and what is interesting that it cannot catch the lower scales of the variability, and because of this, we need attention, and then we also need the latent space, and that will be addressed by Aman Raju. So actually, we need to pay attention more to the closer points in time, and then, of course, less. And the next one is actually to upgrade to the transformers. Okay, thank you.
Sorry. Ilsan, please.
Yeah, thank you. Have you ever any chance to associate that self-organized map, sort of the cluster, to the specific type of, the EGN, for example, like, for example, binaries or something else, or is it any physical meaning associated with that?
Thank you, Ilsan, because we choose self-organizing maps and neural processes because they are the unsupervised type of the machine learning, because we don't want to rely on our background knowledge a lot, and self-organizing maps has been applied in the other types, galaxies and objects, and we will see how it is going on with stratification within the AGN. For now, we can see stratification of the variability, but as for the binary, that is a good point to check.
Thank you very much. We have to move forward. I got very strict instruction by the SCOC chair that we have to. So we move to the next talk by Aman Raju, who is going to present the upgrades of the package that was just presented. So, Aman.
Like this? Can you all hear me?
Say it again.
Can you all hear me?
Yes.
Okay. Huh.
Just like do, and we will move it or something like that.
Maybe you can open the PDF. I've also given a PDF.
You don't have any.
No. No, I have the GIFs. Do you think those would work on the PDF?
Okay, that's something. Back to the. Yeah. Maybe better than the because it has because it's not duplicate. Okay. Yes.
Mm-hmm. You said on the top?
On the left. We don't see that.
Ah, okay.
Yeah.
Thank you.
I don't know. Thank you.
Okay, hi everyone. I'm going to be building on the talk and the work that Eva did and show you some of the updates that I've done to the QNPy package. So just a short list of the other methods to model quasar variability. You have parametric as a base of modeling, which include that damped random walk, and other updates to that using Gaussian processes, general Gaussian processes, or specific algorithms. Then there are also non-parametric assumptions, which a few of the people here have worked on. And we are trying to develop a package that also works in a data-driven non-parametric way without prior assumptions on the curves. So, and within the LSST in particular, there's going to be a large data set. So we want models that are flexible enough to adapt to large data points. And of course, since we're going to have many new objects that we haven't seen before, we don't want to be biased by previous assumptions. And the LSST will provide us many observations with very short cadence periods, but will have large gaps in the data. So we'll want to train our models to understand how things work on short scales, but still be able to fill in the gaps. And we also want models that can learn from very few data points so that we can start modeling within the early years itself. And that's why we have our QNPy package, which you can check out with a simple pip install or the GitHub. We recently published the 0.0.2 version, and we've put the workshop for that online, where we've integrated the self-organizing maps that we described in the previous talk, and they work in tandem with the processes. Currently we're trying to test it on many different data sets with the optical, and we're planning to try X-ray data with Swift, and we have a few different publications. The original ones by Eva, the 2023 paper where we applied it to the LSST AGN data challenge, and the new ones, the one published by Eva on the classifiers, and we're currently publishing our package in the Journal of Open Source Software. So I'm going to talk about the few upgrades that we made. First, just a short description of the self-organizing maps with results from the LSST AGN data challenge. We use the clustering because it can partition our data sets into smaller samples and also more representative samples. We have a good model like self-organizing maps. Here's just another basic idea of how to work. they can use different nodes in a grid-like structure in order to capture dependencies on the data using some sort of metric, like a Euclidean metric, and update it based on different hyperparameters like the learning rate or neighborhood function. We include a lot of different hyperparameters, and some have been found to work better than others, especially the learning rate and the sigma function. We've included a lot of different editors also, so we can understand how well our models are working. And you can see in these graphs here, we can actually tune our SOMs in order to get the best results and try to see the difference between methods that generate lots of items per cluster versus ones that generate more clusters with less items each. And here's the results from the ATN data challenge, where we found that we can get clusters that have distinctive flares or dips in each of them. Then the next step is to actually upgrade the neural processes themselves. So here, what we did is in a process, what we're trying to do is encode the light curve into some sort of representation, the entire light curve, and use that representation to model the target points. However, when you add attention, you can actually tell it how much of the representation to use for each target point that you want to make. That allows you to actually capture the effect of each point on the other points themselves instead of an average representation. And just as a brief description, attention assigns weights to different parts of your input sample, like a sentence or a time series, and how much they relate to others using a simple dot product. Or if you want to be more fancier, you have multi-headed attention, which is implemented in transformer models. So when we trained it on light curves from the LSST AGN data challenge set, we got a lower loss for models with attention, and even visually, you can see that it can actually understand the entire structure of the light curve better and capture more points with the model than before. Then finally, we have the latent space, which we added in order to get a much better understanding of the light curve. With the latent space, we incorporate from a variational autoencoder in order to get a better global representation and also draw different samples from the representation. So what samples means is, so in a variational autoencoder, you just encode your input, and then you get some sort of mean and standard deviation, and use that to produce different samples. You can do that for many different types of data, like text or numbers or pictures or light curves. And so in neural processes, we try to keep these two parts separate. We have one that focuses on the attention and one that focuses on the latent space in order for getting both the global and finer results of the features. And you can see the ones that have both attention and the latent space have provided much better results and trained much more quicker, the green curve on the top left. And they're able to understand our light curves better. We can generate samples where there's different ways of training them. We can train it on a large number of samples or train it on one and try to keep the representation accurate. And we have different methods of doing this. We also looked at short-term variability, and it was able to capture just distinct seasons of the light curve better than conditional neural processes. And finally, we wanted to see if we can recover parameters as well from the light curves. So what we did is we simulated a few different light curves by involving a down random walk with the transfer function. We tried it with just the Gaussian transfer function at typical time lags for the LSST filters. And we also tried it with the thin disk lamppost model, which actually contains characteristics of the black hole, such as the mass, the Eddington luminosity ratio, the inclination of the black hole, and so on. And we tried to see if we can actually look at the hidden representation and extract this information from it. So what we did is we added an extra layer inspired by Park et al. 2021, where we added an MLP that takes the hidden representations and generates the transfer function or any of these other parameters and try to train the model to learn this. So when we tested on Gaussian, we found in a lot of different bands, it was actually able to recover the transfer function that we had involved with the damped random walk. In some cases better than the other. And then we also tested it on the more parametric transfer function. And again, here we were able to recover it in a lot of cases and still at least follow the shape of the transfer function. We also checked if it could recover the parameters themselves, and we found that in general it does tend to recover the peak, the distribution, and can also reproduce double distributions as well. So our next steps is to test this out and try to create different transfer functions and train different models on each. And then once they're trained, we can try to see if it can recover these transfer functions from real light curves as well. We also want to try using the clustering before the simulated light curves to see if that has improved the effectiveness. Increase the sample size. We just use the 100 and the ones I produced. A larger sample would give us better results. And other analysis of the lattice space. For example, we're working on PCA analysis of this reconstruction and seeing what are the different light curves that it can generate in this lattice space. And here's my references and just a short summary of the entire QNPy pipeline. Thank you.
Thank you, Aman, for perfect answers to questions.
This is super impressive. Can you go back to the parameter, like the physical properties you were showing?
Here.
So this is the blue is the input. Sorry,
So the orange is the actual distribution. This is still a small sample because it's just the test light curves from the 100. But even with this, the blue ones are predicted ones and the orange are the actual.
Have you checked, not in a histogram, but like in a scatter plot, you follow the one-to-one prediction?
No,
Because-
we haven't checked that. So you mean like a corner plot between these
Yeah.
different parameters?
Also, because I've seen some works where if you don't help the space to learn the physical properties, it's hard to get relations. So maybe just a suggestion would be to use weakly supervised learning, where for the
Yeah.
small set you force the latent space to correlate with physical properties. I can send you a reference paper.
That would be nice.
Thank you very much, Paolo, for all input. Any other questions? Oh, yes, please.
So I have a question about the transfer function. So currently, how many filters do you?
So we're working with this 5D with the wavelengths in the LSST. We're using the UGRIZ forms.
What if the transfer function is the real transfer function type of model? And how do you deal with that?
You mean if you don't have the function?
The model
Mm-hmm.
is the Thindics lamppost, but what if the universe doesn't follow that?
Okay. Yeah, so there's two different approaches we were thinking of. One is we just we keep training this MLP, and once it's trained, we actually apply it on real data and see if we can actually recover the same sort of transfer function. Another is to actually decouple this from the training and then train it after we've trained the model to reconstruct the light curve. So you can train the neural process itself separately and then have a separate MLP that you can attach to it for a different range of different transfer functions and see which one matches your real data better.
Thank you very much. If there are no further questions, thank you once again. And we move forward with Joshua Fagin, who is going to continue in this avenue of deep modeling of quasar variability using latent stochastic differential.
Okay. Thank you. So as you said, my name's Joshua Fagin. I'm entering my 5th year of my PhD at the University of New York, and also this is in collaboration with James Chan and Henry Best, who will give great talks later today and tomorrow. And my work is deep modeling of quasar variability using latent stochastic differential equations. So we all know what quasar variability is. LSST is set to observe tens of millions of quasar light curves in 6 different optical bands, but those light curves will be kind of sporadically sampled across different LSST filters, and there'll be long gaps of missing data. So our machine learning techniques need to be able to handle those challenges. And how do we model quasar variability? The most common technique is to use Gaussian process regression. So an example is shown here for a 20-year light curve. But Gaussian process regression requires choosing a specific form for our Gaussian kernel, usually damp random walk kernel, for example. And then we can optimize the parameters of that kernel using some kind of method like MCMC. But the problem with doing this for LSST, it's difficult to use for multiband data. We expect each filter to be highly correlated to one another, and we want to kind of correlate kernels of this Gaussian process. And it's also very difficult to apply to the tens of millions of quasar light curves we expect from LSST, since doing that MCMC sampling to get posterior on our kernel parameters is very computationally expensive. So introducing one particular machine learning technique that can model quasar variability, latent stochastic differential equations. So latent SDs are a generative deep learning method that can model continuous time stochastic dynamics. This is just a very simple example where a bunch of latent SDs are fed to some sinusoid. But in general, we're solving this equation here. The details aren't very important. It's a first order stochastic differential equation. And I just want to point out that this diffusion and drift term now, these functions are going to be replaced by neural networks instead of some analytical function. And our overall goal is to use latent SDs to model the quasar variability, fit the time series, and also simultaneously predict the accretion disk properties and variability properties. And so I'll briefly go over our actual model for the accretion disk and so on. So we model the AGN as this lamppost plus thin disk model, essentially where we have a corona above the supermassive black hole, illuminates the accretion disk. We expect higher temperatures in inner regions of the disk and lower temperatures further away. So we get a bluer light near the supermassive black hole, and redder light farther out. So mathematically, we represent this reprocessing on these transfer function kernels here, dotted lines with the time lags we expect from each of these units. Whoops. Thank you. So yeah, in this figure here, we have this intrinsic variability, and then mathematically this as a variability kernels that shifts over our optical light curves, and then click on that, and then it smooths out and thank you. So kind of the simplest model we could use for the driving variability is some damp random process. Slightly realistic models, but the equation here, again, the details aren't really important, but this is a first order stochastic differential equation and sort of motivation for using this neural networks. And we expect that to kind of follow these SDs. Why not use neural networks that can be well represented by stochastic differential equations? So here I just showed two different examples of the driving variability with different characteristic timescales or random tau. And here's a bunch of transfer functions. Basically, we can the driving signal with transfer functions to simulate our light curve. Just to show the parameter space, the most important feature is your black hole mass. That's the main determiner of the time of the variability. But we also have many other parameters like the black hole spin, inclination angle, the edge ratio, redshift. Also, I want to point out temperature slope. So we actually vary the temperature slope. This could be interpreted as like a wind model, which our collaborator will talk about more tomorrow. But so we actually deviate from the model and also the corona. And so, okay, we simulate our light curve, and then we actually want to impose LSST like cadences and noise properties and model simulated LSST light curves. So basically, I just take a bunch of random points in the sky using Rubin sim to get their 10-year observation strategy my training set. So the blue context points, those are the observations of LSST, and then the black dotted line is our simulated light curve. So here is kind of a brief overview of the architecture of the neural network. Come talk to me after if you want me to go through it in detail, of course. But basically, this works similar to a variational autoencoder. We have this encoding section, so we encode the observations down to some context using RNN, which is a recurrent neural network. Then we predict the median standard deviation of our latent space. This is the latent part of our latent ST, which we can sample from, which is our SD solver. And then we project that to a median standard deviation for output space to best reconstruct the light. And then at the same time, we can predict the full posterior distribution for parameters of interest. So showing an example of what this model can do. On the left, we have a latent SDE predictions. So it's a little different, but orange, there's a mean and then 1, 2, and 3 sigma standard deviations of the reconstruction. And then I show the exact same thing for a multi-output Gaussian process regression baseline. So it should be more of a fair comparison. The Gaussian process actually works on multi-band data in this case. And they look quite similar, but we actually go and benchmark this across a test set of curves, and we find that our latest model outperformed the Gaussian process regression baseline across all our different metrics here. While of course being very fast, we could quickly apply this to the entire LSST sample, for example. And here's an example predicting the parameter space. I just zoomed in on a few of the parameters: the black hole mass, the time scale, the variability, and the structure, the standard deviation of the different one. And here I show the mean values versus the true values for each of the parameters. Like I showed earlier, the mass, variability parameter. Also, there's some predictive power for the temperature slope and the inclination angle. And so that was kind of the first generation of our latent SD model. And my next steps are actually building auto differential simulation of the accretion disk. I show this just to show that it's a 2D simulation of the disk, and this is all written in PyTorch. So basically, it works on the GPU and can actually be incorporated into our model. And that's what I do. I incorporate the physics of this into the actual model. So instead of before, where I was predicting the light curves in our UV optical bands of LSST, now I am only predicting the driving variability. I predict the parameters of transfer functions and go through the auto differential simulation to produce these transfer functions. I actually perform this convolution within the architecture of the neural network, kind of forcing the physics into the neural network itself, making it more interpretable for us. And that also allows us to use some fancy new machine learning techniques. I'm trying to use inference here where now we can iteratively adjust the parameters of the accretion disk and parameters of the latent state of our SD. We perform this convolution in the architecture of our neural network, as I mentioned, reconstruct the light curve, and then compare that to the observation points, use this recurrent inference machine technique to iteratively adjust these parameters for a couple of iterations. And I've shown the preliminary results that this has improved the performance of our model when compared to only doing this for a single. And now, as I mentioned earlier, we can actually reconstruct the driving variability. This is kind of similar to what Cream does, for example, where here the blue is the true driving variability used in the simulation, and this orange dotted line is our reconstructed driving variability. And places like this are places where there's seasonal gaps, so there's basically no information. So we just tend toward the mean distribution in that case, but focusing on this area, for example, where we do have observations in between those season gaps, we can reconstruct the driving variability. And we also reconstruct the actual transfer functions, right? Because those parameters are converted directly to transfer functions. And so we can see here the blue is the true transfer functions, and the orange is the best reconstruction of our model for each of the LSST bands. And from those transfer functions, we get mean time delays directly. So this is all self-consistent. We predict parameters, we get transfer functions, and then we get time delays, and then we predict uncertainty on top of those time delays. So we get kind of each of these, we get a predictive time delay for each band. And I want to also mention that we're making improvements to our simulation. So now I'm actually modeling the quasar spectrum to get the mean brightness of each band, which is not something I was doing before. So this is an example here. We have the continuum comes from our accretion disk model, and then we add different features like the quasar spectrum, the emission lines. Sorry, we add the emission lines, the host galaxy contribution, and extinction on top of that. Actually integrate that with the LSST response functions to get the mean brightnesses of each band. And that gives us information related to the redshift, for example. We could actually have some predictive power on the redshift now, since we know information on the brightnesses of each band. So this is very useful for photometric redshift prediction, and also predicting the Eddington ratio. And we also switched to a broken power law driving variability instead of the random walk. It's more realistic to predict the break frequency of that broken power law. So in conclusion, our latent SD models, they're better and faster than typical Gaussian process regression. There's big applications to anomaly detection using that latent space of latent SD. These auto-differentiable simulations can inject physics within the architecture of our neural network. And our auto-diff simulation is at least an order of magnitude faster using GPUs that can be open source. So that will be useful for other methods as well, like using MCMC and also Hamiltonian MCMC. And I'll mention now, before someone asks, we'll be testing this on real data very soon and comparing predictions of our model black hole mass to estimates spectroscopic data, for example. So, thank you.
Thank you very much, Joshua. Wonderful talk. And if you don't mind, please, I'm going to give the first the microphone to Lee, because
Hi, great talk. Thanks. I have a question about your black hole simulation. Can you talk a little bit more about that? Like just like what goes into it, what exactly it tells in the simulation?
Yeah, sure. So I use kind of the Novikov Thorne model for the disk plus the lamppost And yeah, I've been working on making some improvements, including some kind of approximations to GR effects, the redshifting of light from the curved black hole, for example. But so far, I found it not to make much of a difference um, in terms of the time scales that we care about in LSST for reverberation mapping.
Jennifer, do you have follow-up? No.
Thank you. This is very interesting. I have a very naive question. So, some part of the optical variability we think is processing from the that is covered by your model, but other, like, we think the long-term large amplitude fluctuations are produced by a different process that maybe doesn't have the same ordering of lags. Does it make any difference if you include additional variability power in your light curve that's produced by the drive?
So that's a good question. I think we don't currently account for that because all of the variability should be coming from the drive signal. I think we do include like host galaxy contribution, but that's not variable flux. And future work needs to be done also including stuff like variability from the VLR and stuff like that isn't currently in the model, so that could contaminate your signal, for example. Thank you.
Thanks. Also, I have a naive question because I really do not know. In all these works of variability, are you also considering photometric errors on the measurement or just the magnitudes? Because this I didn't get.
Yeah, I can't speak for the other models, but I do. Where is it? I do include photometric errors. Some of these points have larger photometric errors than others, but yeah, that's all.
Because that is fundamental, right?
accounted
It's for counting for variability. Okay, thanks.
Yeah.
Thank you. Any other comments or questions? If not, let's thank Joshua once again. Thank you very much. And we move forward with the next talk from Summer McLaughlin, which the talk is going to be on using Gaussian processes to detect AGN flares. So, thank you. I'm going to give you 2 minutes warning. Best way to put this on like this.
Okay. Cool. Okay. Yeah, so my name is Summer McLaughlin and I'm a final year PhD student at the University of Sheffield, working with Malay and Stuart Littlebird. And I'm going to be talking to you today about my research, which is centered around the systematic detection of AGN flares in the era of time domain astronomy and LSST, specifically using a technique called a Gaussian process. So I don't need to tell you guys that the light from AGN is variable, its brightness changes over time, and this variability occurs with timescales of several months to years, as we know, across all wavelength bands. And this variability typically shows an amplitude of a 0.1 of the magnitude timescale of several months, right? It's widely accepted that this variability is caused by the X-ray corona and instabilities in the accretion disk. However, every now and then we observe AGN that seem to deviate from this standard variability behavior, and they do often rapid or extreme brightness changes. Now, the way that people kind of quantify these events varies, but in general, this extreme variability must be statistically significant from the baseline variability, and they kind of point as AGN flares. Now, they're thought to be extremely rare, occurring once every 10,000 to 100,000 years per galaxy, and their origin is not known for sure. So there's some suggestion that they could be caused by the same mechanism as variability. so maybe accretion distance stabilities. But there are a number of alternative explanations, such as tidal disruption events, superluminous supernovae, variable accretion, etc. But this is a really new field, and so they could be by something else entirely. Now, we all know that the study of AGN variability, specifically AGN flares, as well, is a kind of probe of the accretion, direct measurement of accretion, and this allows us to essentially, if we can't resolve the accretion disk directly, we can use variability to kind of probe those innermost processes focused on the black hole. So why is this really timely when thinking about LSST? Well, these things have kind of been touched on already, but for the first time, we're going to be able to actually observe these events in real time as they happen, which is going to allow for rapid follow-up. The other thing is that we're going to be able to probe unprecedented regions of AGN redshift luminosity parameters. So this is going to give us really more varied surveys than we've seen before. And because AGN flares are thought to be so rare, we need huge amounts of data to be able to develop statistically of these. So LSST is going to be able to provide that. Okay, so what has been done before to kind of systematically detect AGN flares? Well, the majority of the literature focuses on individual events that have been detected surreptitiously. I've picked out a few kind of principal studies in this area, and I don't have time to talk about them all in detail, but I just want to kind of mention that the first and the third study are selected based on an amplitude cut, right? So anything above a certain magnitude gets flagged. And the second study is selecting based on the timescale cut. And whilst, of course, there's justification in each case for doing so, it would be nice if we could remove these biases from selection. And so I want to motivate a kind of statistical method for detecting these things, one where you don't have to assume a timescale or an amplitude, or indeed anything about the that you tend to detect. So with that, it's actually quite a difficult problem, right? In that we're trying to detect a transient signal in data that is variable. And so we need a way of kind of quantifying what constitutes significant departure from variability. Therefore, this method must be statistically robust and resistant to outliers due to observational effects and sample data. Okay, so enter the Gaussian process. So Gaussian processes are a statistically robust form of regression, take uncertainties into account, and they are informed by the sparsity of your data. I like to think of them as a statistical way of the dots, right? In the way that it uses something called a kernel function, which is a covariance matrix, and this just describes how points are related to one another, okay? So how your data is varying. And that's the kind of key point of using the Gaussian process in this context, is that it's simply a means of parameterizing the covariance of your data, i.e. variability. And so on the right-hand side is one my Gaussian process fits to a ZDF-like curve. And as you can see, it predicts the general trend very effectively, and uncertainties change depending on how many data points are in a certain region. And so what it's doing is it's effectively learning how variable your data is, which then allows it to make reasonable predictions about regions of sparse. So why would these be useful then when you're trying to detect AGN flares? Well, as I said, Gaussian processes are just a means of parameterizing your covariance and how all of the data points are related to one another. Essentially, what you can do is you tell the Gaussian process the expected functional form of your data. Okay, so AGN variability is stochastic, so you choose a kernel that reflects that, but don't worry too much about the equation. And what you do is you run a Gaussian process on a light curve with this variability kernel, and it will return for you the most likely parameters that go into that kernel, given how your data is varying. Okay, and these are called hyperparameters. And so every individual light curve is going to have its own unique set of hyperparameters depending on how it is varying. Okay. So with this in mind, as I said, if every individual light curve is going to have different variability parameters, different hyperparameters calculated by a Gaussian process, one can imagine simulating normal AGN light curves and AGN light curves that contain flares, and one might expect those variability hyperparameters to exist in different parts of that parameter space. And so that's exactly what I did. I simulated 20,000 AGN light curves with a damp random walk, 10,000 I left alone, and 10,000 I injected with Gaussian flares. I then ran a Gaussian process on these light curves with my variability kernel, and it returns for me the most likely parameters given my data. And so this is where the light curves with normal variability lie, and then this is where the simulated flares lie. So you can see the hyperparameters for flares in this case exist in different but partially overlapping regions of them. And this is good because then it means that we can now distinguish between them, albeit it will never be perfect because of the overlap. But what this means is that because a Gaussian process is robust, I can then calculate the probability that a given light curve contains a flare based on its location within this plot. So you give me an AGN light curve, and if its hyperparameters live somewhere within these distributions, I can tell you the probability of that. So to put it simply, if an incoming light curve lands in the blue distribution, I might say it most likely does not contain a flare. If it lands in the orange distribution, I might say it likely does contain a flare. And if it's within that overlap region, it might be. Okay. So I've touched on the kind of simulated data that I used, which was my set of 20,000 simulated AGN curves, and 10,000 were injected with Gaussian and gamma flares with magnitude amplitudes ranging between 1 to 2.5 magnitudes and widths of 100 to 1,000 days. But of course, in reality, AGN light curves are not uniformly sampled, so we used a 10-day cadence in those simulated light curves, and they contain outliers due to observational effects. And so I take these things into account too by gradually altering my data for it to become closer and closer to what real data would actually look like. I don't have time to discuss all of the steps here, but I think the most insightful thing that we did was we actually injected simulated flares into a sample of real ZTF light to see how the Gaussian process would fare. So here are the results. So on the left-hand side are the hyperparameter distributions for the flares and non-flare space. And as you can see, there is significant overlap. And as such, I've produced a confusion matrix on the right-hand side. What I've done is I've chosen a probability cutoff above which to contain a flare, simply to produce this confusion matrix to show you. But essentially, the true positive rate in the bottom right-hand corner is 88%. So the Gaussian process is correctly identifying flares as being flares 80% of the time. The false positive rate is 10%, so that's the top right-hand corner there. And what that means is that 1 in 10 non-flares is incorrectly being classified as a flare. Now, this is my feasibility study, but of course, looking forward to LSST, when we have huge amounts of data, you probably care much more about the purity of your sample more than your completeness. And so we do want to be looking at getting this on the down for future. But as I say, I've kind of moved from one cutoff in another, in a way, since the probability cutoff produced the matrix. But I would argue it's more statistically robust at this stage than choosing any cutoff a priori. Of course, you can change this cutoff
depending on whether you care more about completeness. Okay, so the final step is to run the Gaussian process on real data and see what happens. So this is the unaltered set of the type 1 ZTF light curves. And the Gaussian process selects 27 of these out of 9,035 containing extreme variability or flares. These are shown on the right-hand side. So while all of them show a kind of typical flare signature, right? They all show extreme variability when you compare them with a sample of 100 randomly selected light curves that were not as extremely variable by the Gaussian process. And it's a bit pale on the screen, but that's what I'm trying to show by the grey light curves in the background. So this has been fairly successful as a feasibility study, right? But it isn't the full picture. Thinking about LSST, there are still some things we might like to know about individual flares, especially when thinking about follow-up. So we want to know when the flare actually goes off, i.e. its location within the light curve. And this will allow us to work out how much data is needed to be able to identify a flare, and how early into the light curve we can say that there has been a statistically significant deviation from normal. So one could imagine applying the Gaussian process in a kind of rolling way, constantly reevaluating as you feed it new data. And that's exactly what I'm showing on the right-hand side. So I start the Gaussian process at 30 data points, and I reevaluate each time I feed it a new data point along the light curve. And this enables me to track flare probability as I go along. And as you can see, this works exceptionally well for a well-sampled simulated light curve. And the really cool thing about this technique is that we can actually plot the path that this light curve takes through that hyperspectral space. And so the flare and non-flare distributions we've seen before for simulated light curves. And as you can see, as more of the flare is elapsed, the hyperparameters move further and further into the flare distribution. Okay. So what's next is I'm obviously going to consolidate and expand this flare localization analysis to the example ZTF curve. And then I would like to expand my sample by using the million equation catalog. And what this will enable me to do is, looking ahead to LSST, it will enable me to kind of embark on a comprehensive study of actually how much data is needed to be able to detect flares in a single light curve, and actually how early into a flare detect it. And to kind of just summarize, our kind of ultimate goal, right, is just to develop a statistical method of detecting AGN flares in large amounts of data. So the idea is that these kind of techniques can be applied to LSST when it has first light. And so I'll just read my summary there and take questions. Thank you very much.
Thank you very much, Summer, for this talk. And I see many hands, and so I'm going to start with Joshua, if that's okay with everyone.
Hi, great talk. I'm just curious why you use the Mattern 3.5 kernel instead of the more common one. I guess it's Mattern 1.5. And also, have you considered using maybe higher order or karma processes? Then you have a few more parameters to do clustering.
Right. Okay. Yeah. So I did. I've got a paper out on this, and we did compare the Mattern kernel to the damp random walk, which as Mattern 1.5, and there's no significant difference in the results. They're all very similar. But as you say, the Mattern 1.5 just happens to be more common. When you say looking into karma models, do you mean to simulate light curves or to classify?
I guess you could use it for both, but I'm more meant to classify. Like if you fit with the karma processes here, you have 2 parameters for your Gaussian process, but karma processes have, I don't know, actually I'm not an expert, but it has more than 2.
Yes.
And then maybe you could use more complicated clustering algorithms. Just a thought.
yeah, no, that's definitely something that I want to look into. I probably won't. I submit my thesis next year, so it's probably something that I would like to do in the future during a postdoc. Is really comparing these different models to see what the best one is. Really.
Thank you, Elson.
Thank you. Great talk. My question might be very naive. I'm very curious in terms, you mentioned the real-time sort of detection of the
Yeah.
flaring, but people also mentioned about the computational speed of that in the parameters of the Gaussian process. Given the so many potential candidates, what is your strategy? Obviously, you will not do everything from the LSST for that process. Do you have any strategic plans, selecting few, promising candidates, doing
Right.
this process in real time?
Okay, so it's a little bit of a kind of misconception that Gaussian processes are very computationally expensive. I intend to apply this Gaussian process analysis to all LSST AGM. The reason why I can do that is because you don't need to use MCMC or particularly rigorous sampling methods when you're just flagging up items for fault work. So when you're modeling AGN light curves, you really care about getting accurate physical parameters out. And so, of course, you want to use techniques like MCMC to get uncertainties on those pointers. I'm doing the reverse, right? So I'm not assuming, I'm not trying to get out any physical properties of the light. I'm simply flagging it up, showing weird behavior. And so what that means is I can essentially get rid of a lot of computationally intensive techniques, and I can just, I can run 20,000 in less than 10 minutes. So I'm not particularly concerned with that.
Thank you. One question here, and
Thank you so much for wonderful talk, and I would like to follow your nice reply on this problem of the complexity of the computation, because there is a nice paper by Tak from the ISSC collaboration in the LSST using the sparse Gaussian processes, specifically also related to this problem, the number of the objects and the available light. So, thank you.
Okay, thank you for that. I haven't seen it, so thanks for pointing it out.
So we have a lot of questions, but I'm gonna give a microphone to another question. And, so it's Maria. Maria, maybe you were.
So what is the best estimate for the rate of flares? The reason I'm asking is this paper by Matthew Graham that associates the LIGO events with AGN flares?
Yeah. Okay. There are a few estimates on how often these are occurring, right? Excuse me. So some people say 1 every galaxy every 10,000. Some people say 100,000 years. The problem is we have such a tiny sample size, and we really do not know how often things are happening. I have done some calculations that kind of thinking about how many we might expect to detect in LSST. It could be anything between 10 to 10,000. But this is a really new field, and I would take all of the kind of predictions of the rate with a pinch of salt.
Thank you very much, Summer. I mean, the audience is like wild for asking questions to you, but I would kindly ask all of you to ask questions during the lunch break and coffee. But we continue now with the last talk of the session. Thank you once again. And big applause. So Weijan Yu is going to conclude the session with scalable and flexible Gaussian process modeling of AGN light curves in LSST, basically answering some of the questions asked to Summer. So Weijan, thank you.
It's on the right. Okay, so for those of you who don't know me, I'm Wei Xiang. I'm currently a postdoc at University in Canada, by Dr. Run. So today I would like to give a presentation on this Canadian income contribution, software income contribution directed to agent science collaboration. And the specific project I'm going to talk about is the scalable and flexible GP modeling of agent LSST. And this project is in part supported by the Download Institute at University of Toronto. So hopefully my talk can sort of address some of the drawbacks of Gaussian process modeling. In addition, I want to make note the project is on its early stage. We hope eventually we will make a tool that is provide alternative options to people who want to do AGN variability analysis. Okay, so we have heard a lot about a Gaussian process. Why, right? The short answer, the one sentence answer is that it produces a power spectrum density that is close to what we observe, right? This is from the Kozlowski paper, but if you make a power spectrum density of AGN light curves, it has some of this kind of characteristic shape. We all know that we refer it to the BRW process. Actually, if you have a kernel that's exponential kernel, have those parameters equal PSD. Okay. Some of you will say there are more recent works showing that the slope of the PSD is steeper than that predicted by BRW. What would you do with that? So if you ask me, I would say go to Karma, but it's not the only option. There are other GP kernels that give you steeper PSD slope. Okay. Hope I have convinced you that GP is a reasonable way going forward to modeling the rate noise variability in AGN. So next, I want to talk about how modeling the rate noise variability using GP fit into the various science cases we would like to do with LSST, right? Starting with selection, also just purely rate noise variability. Regression mapping is rate noise variability plus some kind of lights, and nuclear transients, rate noise variability plus some characteristic, explosions per example, right? That doesn't have to be specifically correct, right? And intermediate mass black hole selections is really probing the short time scale or shorter break time scale, right? Also super massive black hole batteries, you add in period into the rate noise kind of variability. Okay, but they're not low-hanging fruit, right? We want to do this, but there's a lot of challenges. Some example, first and foremost, the data is huge, right? How do I address that? The current data analysis softwares aren't able to handle all of them. The cadence, we have worked a lot on the cadence evaluations for selecting intermediate mass black holes. I think is just too sparse for that purpose. And rolling cadence, people has a lot of thoughts of what large gap is going to do with different science cases. And for DISC-RM, my impression is that people mostly focus on DDS because of the high cadence. But what about fast deep? The agents in the fast deep, the main circuit, we have a lot more agents there. So probably that will be hindered by both the cadence and the scalability to current software. And periodic signals might be confused with the intrinsic stochastic variability. The non-simultaneous observation will make it really hard to come up with color information. Hopefully, the tool that we're working on will address some of the problems and also provide alternative potential. It's not a solution, but ways to relieve some of the tension. Okay, so I will start with the first issue is the data volume problem, and our solution is using the Sledge model coupled with the JIT compilation enabled by JAX. So don't worry about what those means. It just means fast, okay? And how fast the red plot shows give you the answer. So the red plot is the comparison of time it takes to evaluate a single DRW likelihood using different software that's available right now in astronomy. So x-axis, number of data points, y-axis is the time it takes to do a single evaluation of likelihood. So the black one is Javelin, everybody is aware. So this is probably less famous, is Kali, which uses common shooter to do scalable evaluation of karma likelihood. And the green dotted one is my earlier work as part of my PhD thesis, is using disparity to do karma modeling, and the green one is our most recent work using the celerity model implemented. As you can do the comparison, there is from like a factor 10 to a factor 1,000 speed up over Javelin. Okay, and if you see this kind of shaded area on the left, is approximately the lowest number of data points you're going to get for LST, and this is what you would get for DDX, right? So DDX really brings in a factor 10 even above beat up into the main part we are concerned about given the LST data. Okay, you might say, well, a factor 10 is not a lot. Okay, I give you a spoiler alert that this is just the beginning, right? Just keep in mind, remember this talk, and we'll come back to the scalable part of the GPU developing in a little bit. So what else do you get by writing a tool, software in JAX? That's automatic differentiation. You might have heard this word a few times earlier. It's just being faster. And also, like the JAX ecosystem is really rich. It offers you more options to do the work or the inference we want to do. Optimization, sampling, even like really easily to integrate with the deep learning world. Okay, I don't know how often do you come up to the point where you have some astronomers write a tool that does things really awesome, but then you find you stuck with the algorithm they implemented, and you want to replace it with something new, and then you just can't. You have to rewrite their software. And while you write projects, we offer the option, do whatever, choose your favorite. Don't have to be stuck with one. I don't do that job. They do better than me. So more on the flexible side is with this new tool, we can do multi-band GP, which is really hard with earlier tools. And okay, so again, I want to remind you, keep in mind with this plot, and we'll come back to this. So next, we want to talk about what we do with multi-band GP enabled by JAX. So that is the cadence, right? This on the left shows the median internet gap in the G band, which range from 10 days, 26 days, 20 days, right? This is not enough for many science spaces, for example, looking for intermediate cycles. But if you're able to combine data from all bands, you pick at less than 3 days, and there's another peak at 2 days. So that's our goal, to take advantage of all the data in all bands in a really coherent way. Now I'm showing you some results. So we started with some simulations. 5 years long LST curves, break in, 30, 35 apples for UNG. That's basically the median for the most recent database. Median, the min mag is 5, which reflects the size of error bars. Okay. Now I show the results. X-axis is input, the break time to go of DRW, y-axis is the recovered. if you look at the top two panels, that shows if you fit only U band, G band, right? It looks good if you go beyond, let's say, 10 days or 20, 30 days. But there's no way you can recover anything below that. It just flats because you don't have the cadence to do that, which is simple to understand. But if we're able to combine the data across the two bands, you can see we clearly probe below down that to the shortest time, right? Which you cannot single band data. Why it is important? A lot of people cares about looking for intermediate mass black holes. If you make a cut on the time scale, which comes from the red boxes, that's where the intermediate mass black holes lies in the time scale space, right? That's how we can really enable search for intermediate mass black holes in the whole vast. Once we're able to really how I say that, intrinsically modeling multi-band variability in APNs, you will next really reasonable thing to do is to add intermittent lag between them, right? Things I'm wondering, can we do this with this new model? And do some simulation again now, but in G and I band, a bluer band or a redder band. Here shows the 5-year light curve. There's a zoom in. The full light curve that's simulated and just show you that I'm not cheating. Right? There are peaks in there. 5 days, 23.5 max. Here's the recovery lag, the amplitude of the DRW, time scale, and the correlated variability between two bands. And here it shows you can see some kind of statistics. Here, to tell you it's well converged, and this is the number of effective samples. I will come back to this, why it is important. Now is the fun part. It's only 4 seconds. That's 80 faster if you use EMC, right? And how did I come up with the number? I reach the same number of effective samples. That's a real good number to characterize your anxiety gains, right? We have to do apple to apple comparison. Okay, I take longer than I expected. So, but anyways, that's 800 times faster, right? Now, okay, I just do one example. How does it scale to whole parameter space? What's the distribution, a range of decay time scales, a range of lags? It's okay, not too bad. You know, characterize the ratio between the recover one, the input ones, compute some statistics. There's the median absolute deviation, the number of outliers, right? You can see that it increased, it gets better with brighter sources, right? I know we're thinking, how does it compare with Javelin, right? That's the mainstream thing. I did this comparison. Green and Javelin in orange is my results. You can see one thing that we have been showing is that like Javelin cannot really probe that small time scale regime. But the other thing, the ratios, somewhat comparable, a little bit better based on those numbers, but I wouldn't count it, right? What else we can do? Well, just to remind you, is from 3 order magnitude up to 5 order magnitudes faster than Javelin. What else can do? I just heard a talk about transients, and we only model DRW and transient. I simulated this DRW transient light curve. That's the result. I used the model from Graham 2023, amplitude, the transient peak time scale, right time scale, decay time scale, right? And we can do that as well. It's not perfectly centered, but it's close, right? And all MCMC takes 2 seconds. This I think is pretty fast. Others, people cares about periodic signals. I think some similar simulations, added periodic signals. Again, show full light curve tell you that there is periodic signals, and it's like how DRW 50 days, it's 30 days. It's actually very hard to recover those when they are comparable. And the shows that, yeah, we can do that and with well-merged MCMC chain. Here's my last slide. Some takeaways. You're really working hard on this tool that can do both scalable, robust of stochastic variability parameters, multi-band time delay, joint inference of Reynolds variability, transient Reynolds variability, and periodic signatures. So some future work, we'd like to tie some more realistic simulated Likert, for example, lag. Want to use more like based on physical model, not just like a Gaussian lag transfer function. Also use the code later this year. Also look to apply the tool to real data. If you have some ideas, feel free to reach out. Thank you for your attention.
Thank you, Vejan. Really in time for questions. Okay, I'm gonna go first here and then later there. So Jennifer, please.
Thank you. Great talk. This is very interesting and seems like very useful for your future. I have a question about the lag you're predicting. Seems like the lag versus the truth versus prediction lag. You have a histogram and it's skewed towards like the positive side. And can you comment on this? Like, what's going on here?
I don't know. I guess it's just something is in the cadence, right? Because even the combined bands, average lower end is like 3 days. If you go here, see that's mostly due to this, right? It's slightly shifted upwards. Maybe there's just no data point to probe that, right? If you say you can't find here and to the next one, and that's the one there, and it doesn't really correlate with the input lag in a way, in an exponential way. It's just like a constant shift, right? I suspecting that's due to the cadence, that limitation in the cadence. If we are able to combine band data from like all 6 bands, that should improve. I will have the message there, but for that question. Yeah. Yeah. Okay. Thank you.
So this might be the same question, or it might be related. So in your top plot on the left, it seems like towards the right, higher power values seems to be the output seems to be under predicting. Is comment on that, or have you already commented on that?
No, I have not. But,
Okay.
but I thought this is actually a well-known issue. That's one. So your break time scale has to be less than 1/10 of your baseline in order to get correctly recovered. That's pretty well known. This previously corresponds to 1/10. So I simulate like 1,800 days. So that's 180 days around. So yeah.
And I've got one more quick question. Is are you with these kind of analyses, and actually kind of with a discussion element at some point, are we intending to run these in-kind contribution type things on the annual data releases, or are we hoping to do them in real time?
So, yeah, it's a good question, but based on, so I can give a quick answer. Well, not an answer that is, I think it is fast enough to do that. I did a really quick calculation for the lag, the 4-second for you. 1 million Likert that only takes 1,300 CPU hours, which is technically nothing. If you apply for 1 million Likert, right? If you apply for supercomputing time, centers easily get even $100. That's like no money, right? Oh.
Every single night you want 1,300 core hours.
Well, that's a question for
That's
the
a question for
project.
further discussion.
For the project, but
No, I understand.
If I can follow up on that and comment, I don't think the project plans to run software developed data set in real time. Let's put it that way. I mean, they have the set of the products and software they're going to run within the Rubin Science platform. But I mean, it is up to us to see whether we can access data before the data release and test our software. I mean, that's exactly what everyone have, I think, interest in. And final question before we go for a break. I think we have time. Please.
Okay, a comment on that. So it's very hard to convince a broker to run based on real time. Like it's gonna be like for us, it's the maximum time to compute 150 features is 1 second per object in one CPU, and this is only like 4 seconds, one only feature. So it's kind of expensive for a broker. But we can discuss if this is really needed by the community. A question. Sorry if I missed this, but how are you combining the different bands to compute?
That's a good question. So this multi-band kernel, which essentially treat all different bands as not one single process, allow them to vary in amplitude, right? And that's how I get the correlation between the different bands. In terms of the time scale, so if you look at how much does the time scale vary from one band to another in the log scale, is minimal, right? Maybe 0.2-ish dex. That doesn't really, considering the other factors or other error budget that put into your estimation, that wouldn't really affect your estimation, right? Like your benefit is greater than the disadvantage where you assume that's one. That's the answer.
Yeah, well, we keep this discussion later on. I would really like to thank all the speakers once again. Really interesting session. And I want to thank the audience for really productive discussion. Thank you very much.